An interplanetary voyager from a different star system is 3I Atlas. Astronomers characterize this uncommon visitor, the third verified interstellar object ever discovered traveling through our solar system, in that way. 3I Atlas contains secrets from light years away, including frozen ices, alien dust, and maybe even the chemical components of life, which were formed around another star. This is unlike anything that is indigenous to our cosmic neighborhood. Before quietly entering our line of sight, it spent millions, if not billions of years roving the cosmos. It won't last long though. It will shortly be thrown back into the never-ending darkness by its hyperbolic orbit. Because 3I Atlas is more than just a comet, it's a time capsule from another world. Scientists are rushing to unravel every clue it contains before it disappears. What is 3I Atlas? Official designation and discovery timeline. An interstellar object, 3I Atlas is a unique visitor from space. Because it is just the third verified interstellar object ever discovered traveling through our neighborhood, its name bears weight in astronomy. On a hyperbolic trajectory that guarantees it will never return after it departs, 3I Atlas is just passing through, in contrast to comets and asteroids that are part of our Sun's gravitational family. Because of its brief existence, scientists have a limited opportunity to examine a fragment of material that was formed around a different star and was not impacted by the processes that built our own solar system. The official designation breaks down into 3 parts. The 3 identifies it as the third recognized interstellar object, following 1I Oumuamua, discovered in 2017, and 2I Borisov, spotted in 2019. The I stands for interstellar, a classification reserved for objects with clear evidence that they come from outside the solar system. Finally, Atlas references the survey that first detected it. The Asteroid Terrestrial Impact Last Alert System, a sky scanning program designed primarily to look for Earth-threatening asteroids. While Atlas's main job is planetary defense, it has now become an accidental pioneer in discovering alien visitors. The discovery of 3I Atlas was an exciting moment for astronomers. On December 12, 2019, the Atlas telescope system picked up a faint, fast-moving object against the background stars. Initially, it was catalogued as a normal comet, given its faint, hazy appearance. But further observations revealed something unusual. Its orbit was not elliptical, as all solar system comets are, but hyperbolic, meaning it was on a one-time visit, unbound to the Sun's gravity. By running orbital calculations backward, scientists confirmed that this was no ordinary comet. It had entered our solar system from interstellar space, just like Oumuamua and Borisov before it. Interstellar objects are notoriously difficult to detect because they are small, dark, and moving extremely fast. Most pass through our solar system unnoticed. That Atlas managed to spot 3I at all speaks to how sensitive modern sky surveys have become. The Atlas system uses wide-field telescopes in Hawaii to scan the sky every night, searching for anything that moves differently from the background stars. 3I Atlas stood out immediately because of its speed and unusual trajectory. Once astronomers realized what they were looking at, telescopes around the world turned their attention to this alien visitor. Every detail mattered. Its brightness, rotation, shape, and even its subtle color changes could reveal secrets about its origin. Early measurements suggested that 3I Atlas was active, showing a faint coma or halo of dust and gas as it warmed near the Sun. Unlike Oumuamua, which remained mysterious and tailless, 3I behaved more like a weakly active comet, similar to Borisov, though much fainter. But beyond its appearance, the timeline of its discovery is crucial. Astronomers caught 3I Atlas before its closest approach to the Sun, giving them more time to study it than they had with Oumuamua, which was only identified after it was already on its way out. This meant that scientists could watch 3I Atlas as it approached, peaked in brightness, and then faded away, a rare chance to observe an interstellar traveler through most of its journey. Its closest approach to the Sun, or perihelion, occurred in late December 2019, shortly after its discovery. During this period, it became bright enough for medium-sized telescopes to observe, though it was never visible to the naked eye. Astronomers used this opportunity to collect as much spectroscopic data as possible before it dimmed again. By early 2020, its brightness had already begun to drop as it moved away from the Sun, speeding back toward interstellar space. Why does the discovery timeline matter so much? Because time is everything when it comes to interstellar visitors. These objects spend only a short period inside our observational range, often just a few months. Missing that window means losing the chance to study pristine material from another star system, a sample of another world that we can't yet visit directly. The 3i timeline scientists can also learn about the origins of Atlas from its passage through the solar system. Astronomers believe that after being evicted from its home system, it probably traveled across interstellar space for millions of years by charting its journey backward. Its exaggerated path indicates that it originated in a far-off part of the galaxy, but it is difficult to determine where it was born because of gravitational pulls from nearby stars. However, tracking its movement is providing scientists with hints about which star nurseries may have sent it on its protracted journey. Why 3i? The meaning of its interstellar naming. Beyond merely serving as an identification, 3i Atlas, or as astronomers say 3i Atlas, has deeper significance. Where it was discovered, how it was categorized, and why it differs from the many comets and asteroids that make up our solar system are all details that create a tale. The I in its name, in contrast to conventional comet or asteroid designations, designates it as something unique, an interstellar object that was born beneath another star and moved freely around the galaxy before briefly entering our skies. The naming convention for interstellar objects was first introduced after the groundbreaking discovery of Oumuamua in 2017. Until then, no confirmed interstellar visitor had been detected, so there was no official system for naming them. Once Oumuamua was confirmed to be on a hyperbolic, unbound trajectory, the International Astronomical Union, IAU, decided that such objects should have their own classification, separate from solar system bodies. Thus, the I designation was born, standing for interstellar. The numbering is sequential. One I was assigned to Oumuamua, making it the first confirmed interstellar object. 2I was given to Comet Borisov in 2019, the second confirmed interstellar traveler, and now 3I belongs to Atlas, officially making it the third recognized interstellar object ever observed. Each new detection receives the next available number, meaning future discoveries will follow the same pattern: 4I, 5I, and so on. This simple but historic numbering system marks each as part of a small but growing catalogue of alien visitors to our solar system. The second part of its name, Atlas, honors the survey that first spotted it, the Asteroid Terrestrial Impact Last Alert System. The Atlas project, based in Hawaii, was designed primarily to look for asteroids that could pose a danger to Earth. Its automated wide-field telescopes scan the sky every night, looking for moving objects against the fixed star field. In December 2019, these telescopes picked up 3I Atlas as a faint, fast-moving point of light. At first, it was thought to be just another distant comet, but further observations quickly revealed its unusual hyperbolic orbit. Adding the survey name is standard practice for comets and interstellar objects. It acknowledges the team and technology that discovered them, while also providing an easy way for astronomers and the public to associate the object with its origin. In this case, the Atlas system not only identified the object, but did so early enough for follow-up observations, making the inclusion of its name even more significant. So why make such a big deal over the I designation? Because it sets these objects apart from anything formed in the Sun's gravitational family. Ordinary comets are named with a C for comet, and asteroids with a numbered sequence or A. But an interstellar object is fundamentally different. It is a time capsule from another star system, made of materials forged under alien conditions and shaped by processes entirely separate from those of our solar system. The eye immediately tells scientists they are studying something that originated far beyond the Sun's influence. The eye designation also carries with it a deeper scientific excitement. Every interstellar object offers a unique opportunity to study how other planetary systems form and evolve. While we can only send spacecraft to a handful of objects within our own system, these interstellar visitors come to us, carrying with them untouched ices, dust, and possibly even complex organic compounds. A single observation can reveal chemical fingerprints of distant stars, providing rare clues about the diversity of planetary systems across the galaxy. The name also symbolizes how quickly this field of research is growing. Before 2017, no confirmed interstellar objects had ever been detected. Now, within just a few years, we have 3. That might not sound like much, but it suggests these visitors are far more common than we once thought. They were simply too faint for older surveys to detect. The fact that 3i Atlas has joined this short list hints that we're entering a new era of interstellar object discovery, especially with next-generation telescopes like the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, expected to find dozens, maybe even hundreds of such objects in the coming decades. For scientists, the sequential numbering is also a way to build a chronological record of interstellar exploration. In the future, researchers may look back at 1i, 2i, and 3i as the pioneers of an entirely new field of astronomy. Each number represents not just an object, but a milestone in humanity's expanding view of the galaxy. Therefore, 3i Atlas is more than simply a clever moniker. We're admitting that this ice voyager belongs to a brand new historic category that is changing our understanding of how material flows between stars and how planetary systems arise. Every interplanetary item we discover is a communication from another universe, and 3i Atlas is the most recent chapter in that tale. The title serves as both a catalogue entry and a reminder. Where did 3i Atlas come from? Tracing its possible birth system. A tale of dramatic ejections, star migrations, and ancient cosmic history is engraved in the orbit of every interstellar object. Astronomers are rushing to unravel that tale for 3i Atlas before it disappears forever into space. Where did this extraterrestrial traveler come from? That is the key question. Finding its birthplace, or at least identifying the areas of the galaxy it formerly inhabited, may be possible by tracing its wildly inflated orbit backward across space. The process begins with orbital reconstruction. When 3i Atlas was first detected, astronomers calculated its hyperbolic trajectory, a path unbound to the Sun, confirming it as an interstellar visitor. Unlike elliptical orbits, which loop around the Sun, hyperbolic orbits indicate an object is simply passing through, pulled slightly by the Sun's gravity before continuing on its journey. By mapping this orbit backward in time, scientists can estimate the direction it entered the solar system and project its possible path through interstellar space. Interstellar objects travel for millions, sometimes billions of years, and over those timescales, even tiny gravitational nudges from stars, giant molecular clouds, or passing planets can drastically alter their course. For 3i Atlas, astronomers have reconstructed its incoming direction to a broad region of the sky, but pinpointing a single birth star is almost impossible without perfect knowledge of its past interactions. Current calculations suggest that 3i Atlas likely came from a region of the Carina or Scorpius constellations, rich in star-forming activity. These areas of the Milky Way are home to massive stellar nurseries, where stars and planets are born in dense molecular clouds. Interstellar objects like 3i are thought to originate in such environments. During the early stages of planetary system formation, gravitational interactions, especially with giant planets, can sling comets, asteroids, and planetesimals out of their home systems entirely. Over time, these ejected objects drift through interstellar space, becoming galactic wanderers. For 3i Atlas to reach our solar system, it may have been traveling for tens of millions of years or more. Unlike comets native to the solar system, which orbit regularly, Interstellar objects roam on random paths shaped by the gravitational pull of passing stars. Some simulations suggest that before arriving here, 3I Atlas may have passed through other star systems, each encounter subtly altering its trajectory. These flybys could have heated its surface slightly or deposited new dust, leaving chemical fingerprints that astronomers are now trying to read. The ambiguity in galactic dynamics is what makes tracking its birth system so challenging. Stars drift, spiral arms revolve, and stellar orbits are reshaped by gravitational tides from giant clusters, all of which contribute to the Milky Way's perpetual motion. Rewinding the motion of 3I Atlas and its possible source, stars across tens of millions of years, presents massive error margins, even if astronomers are aware of the object's current velocity and orientation. The results are less definite the further back they trace. Most interstellar objects are thought to originate from planetary ejection events. In young planetary systems, giant planets like Jupiter often act as gravitational slingshots, flinging comets and icy bodies into interstellar space. In some cases, planetary collisions or close stellar encounters can violently eject debris. 3I Atlas may very well be a fragment of a shattered exoplanet or a leftover piece of a young system's protoplanetary disk. Studying its composition can also hint at its origin. If its ices are rich in carbon monoxide or carbon dioxide, it likely formed in the cold outer regions of a planetary system, similar to our Kuiper belt or Oort cloud. If it contains silicate-rich material, it might have come from a warmer, asteroid-like region closer to its home star. Early spectroscopic analysis suggests that 3I Atlas has a surface rich in volatile ices, meaning it probably formed far from its parent star in a frigid outer disk before being ejected. The fact that it shows weak cometary activity, a faint halo of gas and dust, suggests it still has some fresh, unaltered material beneath its surface. This makes it a valuable time capsule, preserving conditions from the time and place of its formation. Comparing its chemical makeup to that of Oumuamua and Borisov may reveal whether it came from a similar type of system or an entirely different kind of stellar nursery. A hyperbolic orbit, proof it's not from our solar system. The mathematics of 3I Atlas's orbit plainly tells the narrative of its extraterrestrial origin. Thus, it's not only conjecture. Its hyperbolic trajectory is the most compelling proof that it is not a member of our solar system, even though its ice surface and peculiar chemicals suggest an interstellar history. In contrast to comets and asteroids orbiting the Sun in elliptical or circular paths, 3I Atlas is traveling on a hyperbola, which guarantees that it will only make one visit and never return. An interstellar traveler's cosmic signature is this trajectory. Objects formed within the solar system are tied to the Sun by gravity. Their orbits, whether circular, like many planets, or elongated ellipses, like most comets, are closed loops, keeping them trapped for millions or even billions of years. Even the distant comets of the Oort cloud follow elliptical paths, taking thousands of years to return, but still bound to the Sun. A hyperbolic orbit, however, is fundamentally different. It is open-ended, a one-way ticket in and out of the solar system. Any object on such a trajectory is moving too fast for the Sun's gravity to capture, confirming it was not born here. For 3I Atlas, astronomers measured an orbital eccentricity, a key parameter that describes the shape of an orbit, of greater than 1.0. Eccentricity values less than 1 correspond to ellipses. Exactly 1 describes a perfect parabola, the borderline of being bound, and greater than 1 means the object is truly hyperbolic, destined to escape into interstellar space. The measured eccentricity for 3I Atlas is well above 1, leaving no doubt that it came from beyond the Sun's domain. Its velocity also tells the same story. Long before it even approached the Sun, 3I Atlas was traveling at speeds far too high to be a native comet, merely perturbed from the Oort cloud. Native comets, even when kicked inward by gravitational nudges from planets, typically move at a few kilometers per second, relative to the Sun when far away. But 3I Atlas entered our solar system already moving at interstellar speeds, tens of kilometers per second, indicating it had been traveling freely through the galaxy long before encountering us. When it approached the Sun, its speed increased further as it was pulled by solar gravity, briefly accelerating as it passed through the inner solar system before slowing again as it moved away. But even after accounting for this gravitational slingshot, its outbound velocity remains far above the solar escape velocity, confirming it was never gravitationally bound. Astronomers also compared its incoming direction to models of Oort cloud comets. Occasionally, comets within our solar system can be nudged onto slightly hyperbolic paths by close encounters with Jupiter or Saturn. But these are near parabolic and barely above an eccentricity of 1. 3I Atlas's trajectory is far more extreme, impossible to explain by any planetary interaction within the solar system. The only explanation is that it entered from interstellar space. In addition to demonstrating its extraterrestrial origin, studying its orbit provides hints about its history. Scientists are able to determine how long it has been traveling by meticulously retracing its trajectory across space. According to current theories, it could have been evicted from its host star system during its early chaotic development era and been traveling for tens of millions of years. The strong gravitational forces that originally threw it into the void between stars are preserved in its hyperbolic orbit, which is effectively a relic of that ejection event. The hyperbolic motion of 3I Atlas differs from that of the 2 interstellar objects that were previously found. Whereas Comet Borisov acted more like a normal active comet, Oumuamua had an odd tumbling motion and no discernible tail. 3I Atlas lies in the middle. It is more like Oumuamua in terms of its exaggerated excess speed, but Borisov in terms of its orbit and weak coma. We have a tiny but expanding statistical sample of what is out there because of this diversity, which implies that interstellar visitors originate from a range of settings and ejection methods. How fast is it traveling? Record-breaking entry speeds. One of the most obvious clues that 3I Atlas is an extraterrestrial visitor is speed. Seldom do solar system-borne objects reach speeds high enough to defy the gravity of the Sun. As evidence of its catastrophic expulsion from another star system and its protracted voyage across interstellar space, 3I Atlas did not just escape. Rather, it charged in at a speed that was far faster than anything found in our planetary family. When astronomers measured its velocity, they found that before it encountered the Sun's gravity, 3I Atlas was already traveling at an interstellar inbound speed, v, of roughly 26 to 30 kilometers per second relative to the Sun. That's significantly faster than the typical orbital velocities of most solar system comets, which often move at only a few kilometers per second when far from the Sun. Its hyperbolic excess velocity, the speed it retains even after escaping the Sun's pull, is what marks it as truly unbound. As 3I Atlas approached the Sun, it accelerated under solar gravity, reaching even greater speeds at its closest approach, or perihelion. Estimates suggest that at perihelion, it reached velocities of over 60 kilometers per second, racing through the inner solar system before slingshotting back outward. Once it leaves the Sun's gravitational influence, it will settle back to its original interstellar cruising speed as it drifts away into the galaxy. However, why is this speed so important? How things reach such velocities is crucial. Solar system objects are born with orbital energy connected to the gravity of the Sun. Even comets from the far-off Oort cloud usually return to their lengthy elliptical orbits after being pushed inside by passing stars or massive planets. Even when they are sometimes high close to perihelion, their velocities are still constrained by the Sun's gravitational pull. 3I Atlas, on the other hand, had to have come from far beyond our solar system because of its tremendous inbound velocity, which allowed it to approach with considerably more energy than any gravitational interaction could produce. Dramatic events in its native star system are the only way to achieve this type of speed. The majority of astronomers think that the chaotic early phases of planetary formation are when interstellar objects like 3I are expelled. Smaller rocky and ice bodies are dispersed across their systems by the gravitational slingshots that massive planets produce during their formation. Some are hurled outward, reaching escape velocities that cause them to wander into interstellar space, while others are propelled inward, where they clash with the star or other planets. Over time, a population of free-floating passengers like 3I Atlas is created by the debris that stars release as they move around the galaxy. 3I Atlas's velocity also tells us something about how long it has been wandering. At interstellar speeds of 26 to 30 kilometers per second, it would take millions to tens of millions of years to cross from one stellar neighborhood to another. The odds are high that it has been traveling for a very long time, possibly since the early days of its home system's formation. Some simulations even suggest that interstellar objects may pass through multiple star systems over their lifetimes, each gravitational interaction subtly altering their speed and direction. When compared to the two interstellar objects discovered before it, 3I Atlas falls in an interesting middle ground. Oumuamua entered the solar system at about 26 kilometers per second, while Comet Borisov moved at around 32 kilometers per second. All three objects share similar high speeds, reinforcing the idea that interstellar visitors are ejected violently and travel fast enough to break free of their home stars forever. Its rapid transit also explains why catching and studying interstellar objects is so challenging. These objects spend only a brief time within observational range, racing through the solar system in a matter of months. By the time astronomers confirm their interstellar nature, they are often already moving away and fading. For 3I Atlas, its discovery just before perihelion was lucky, giving researchers a slightly longer window to study it. But even then, its speed meant it brightened and faded quickly, disappearing from view for most telescopes within a year. Another concern brought up by 3I Atlas's rapid motion is if we might ever send a probe to intercept such an object. The answer is no, given the state of propulsion technology today. It would take a tremendous amount of energy and exact time to capture an interstellar object traveling at tens of kilometers per second. For upcoming encounters, mission concepts are being created nevertheless. It may be feasible to send fast-response spacecraft to intercept these visitors if we are able to identify them sooner, maybe years before they arrive. First telescope to catch it, the Atlas survey's role. Modern sky scanning equipment created for a very different reason led to the discovery of 3I Atlas, not a fortunate chance. To save Earth from possible asteroid crashes, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, was constructed. However, this planetary security system accomplished an unexpected feat in December 2019. It was the first to identify a passing interstellar traveler before it disappeared back into space. The ATLAS project was developed by the University of Hawaii and funded by NASA as part of its Planetary Defense Coordination Office. Its primary mission is straightforward: scan the entire night sky every night in search of near-Earth objects, NEOs, asteroids and comets that might pose a danger to Earth. The system uses wide-field Schmidt telescopes capable of imaging large portions of the sky at once. These telescopes aren't the largest or most powerful in the world, but they are incredibly efficient at spotting moving objects. ATLAS currently operates 4 telescopes, 2 in Hawaii on Mauna Loa and Haleakala, and 2 in the southern hemisphere, in Chile and South Africa. Each telescope scans the sky several times per night, automatically flagging any object that shifts against the background stars. Most of the time, these moving points of light are harmless main belt asteroids or known comets, but every now and then, something unusual appears, something moving faster or on a strange trajectory. On December 12, 2019, ATLAS detected one such unusual object. Its automated software flagged a faint point of light that moved slightly faster than typical comets. At first, astronomers assumed it was just another ordinary comet approaching from the outer solar system. and it was catalogued under the provisional name C2019Y4 Atlas. However, as more observations came in over the next several days, something odd became clear. Its orbit did not resemble that of a long-period comet. A hyperbolic route was indicated by an eccentricity larger than 1, according to preliminary orbital estimates. Astronomers from all around the world took notice of this right away, since these orbits are nearly always connected to interstellar particles. As more observations honed its trajectory over the course of many weeks, it became evident that this was not your typical comet, but rather an interstellar visitor, the third ever found. After 1I Oumuamua and 2I/Borisov, it became the third verified interstellar object, when its designation was formally changed to 3I Atlas. What makes Atlas's discovery remarkable is the timing. Both Oumuamua and Borisov were discovered relatively late in their journeys. Oumuamua, for instance, was only detected after it had already passed perihelion and was speeding out of the solar system. By contrast, Atlas caught 3I Atlas before its closest approach to the Sun, giving astronomers precious extra weeks to observe it at increasing brightness. This early detection allowed for more comprehensive follow-up observations, including spectroscopy, light curve measurements, and attempts to estimate its composition. The Atlas telescopes are perfectly suited for this kind of discovery because they are designed for rapid wide-field surveys. Unlike larger telescopes that focus on deep, narrow fields of view, Atlas trades depth for speed and coverage. It can scan the entire visible night sky every 2 nights, making it ideal for detecting fast-moving objects before they fade or disappear. After Atlas flagged the object, other observatories around the world quickly joined the effort to study it. The Pan-STARRS system in Hawaii, the Gemini Observatory, and even the Hubble Space Telescope were enlisted to monitor 3I Atlas's brightness, color, and tail activity. International collaboration sprang into action, coordinating observations across multiple wavelengths, from visible to infrared. Without Atlas's initial detection, this worldwide effort might never have been possible. The detection of 3I Atlas also demonstrated how much sky survey technology has advanced in just a few years. Before 2017, no interstellar objects had ever been spotted, not because they didn't exist, but because we lacked the ability to find them. They are small, faint, and incredibly fast, making them difficult to track unless surveys scan wide areas with high cadence. Atlas's success shows that with modern systems, we are now entering an era where such interstellar visitors may be detected more frequently. Scientists' perspectives on future interstellar detection have already been impacted by the discovery. Next-generation surveys, such as the Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory, are anticipated to discover many more if Atlas, with its comparatively small telescopes, was able to detect 3I. Every few nights, LSST will survey the whole southern sky with its enormous 8.4-meter mirror and broad field of view, pushing detection limits to lower magnitudes and early phases of the approach of interstellar objects. Color and reflectivity, what its surface tells us. Astronomers used color and reflectivity measurements, two of the most crucial diagnostic techniques in planetary science, to determine whether 3I Atlas was indeed an interstellar object. We can only examine distant interstellar visitors by examining the sunlight they reflect, unlike missions that can directly sample the surface of nearby asteroids and comets. Each shade of hue and little variation in brightness provides a chemical information about the material of the thing and the environment in which it arose. When Atlas and follow-up telescopes first observed 3I Atlas, it appeared slightly bluish-green, a common hue for comets rich in volatile ices. This color suggested the presence of cyanogen, Cn, or diatomic carbon, C2, in its coma, gas that glows greenish-blue when illuminated by sunlight. These molecules are typical in comets that originated in cold outer regions of star systems, where ices can form and remain stable for billions of years. The color alone immediately placed 3I Atlas in the category of icy, volatile-rich bodies rather than rocky, asteroid-like ones. Its albedo, or reflectivity, also provided valuable information. Astronomers estimated that 3I Atlas reflects only a small percentage of sunlight, roughly 4 to 10%, comparable to the dark, carbon-rich comets of our own solar system. A low albedo suggests a surface coated in organic-rich dust or carbonaceous material, likely accumulated over millions of years of interstellar exposure to cosmic rays. As high-energy radiation bombards the surface, simple ices can transform into complex organic compounds, creating a dark, reddish crust. However, 3I Atlas also showed something unusual. Its brightness fluctuated slightly over time, even beyond what would be expected from cometary activity. These light curve variations hinted at an irregular shape or surface pattern, with some areas reflecting more sunlight than others. This could mean its surface is not uniform. Some patches may still contain relatively fresh, reflective ice exposed by recent sublimation, while other regions are coated with darker, weathered material. Comparisons with other interstellar objects further highlight its unique surface. Oumuamua had an unusually reddish metallic hue, likely due to extreme space weathering, while Borisov had a classic comet-like coloration, similar to long-period comets from our Oort cloud. 3I Atlas seems closer to Borisov in its icy, volatile-rich surface composition, though its faint activity suggests it may have a thicker crust of processed material that partially insulates its ices. The color and reflectivity also tell a story about its long journey. Objects traveling through interstellar space endure cosmic weathering unlike anything solar system comets experience. Over millions of years, cosmic rays, micrometeoroid impacts, and interstellar dust collisions gradually alter their surfaces. Dark organic films build up, and volatile ices buried deep inside remain preserved, shielded from the harsh radiation. The fact that 3I Atlas still shows some active outgassing when warmed by the sun means that its interior ices have remained relatively untouched since its ejection from its home system. Spectroscopic analysis of its reflected sunlight revealed water ice and carbon monoxide, two common ingredients of solar system comets. But the ratio of these ices to other compounds may differ, hinting at a formation environment around a different type of star. For instance, if 3I Atlas has unusually high levels of carbon monoxide relative to water, it may have formed farther from its parent star, in a colder, more distant region than typical Kuiper Belt objects. Detailed comparisons of these ratios with known solar system comets are ongoing, as even small differences can reveal whether it formed around a sun-like star or a cooler red dwarf. Its age as an interstellar wanderer can also be inferred indirectly from its reflecting qualities. A reasonably bright ice surface would indicate a recent ejection, but a very dark, extensively weathered surface would suggest exposure of millions or possibly billions of years. Three-eyed. The modest reflectivity of Atlas suggests a lengthy voyage, but not one that is so severe as to eliminate all volatile activity. Tens of millions of years ago, it could have been expelled from its home system, which allowed it to accumulate its black organic-rich layer while preserving the frozen material underneath. Studying its hue is like peering back in time for astronomers. The many circumstances under which planets and comets develop across the galaxy are represented by each interstellar object that we see. Our understanding of how special or common our solar system is will improve as we identify and compare more of these visitors. How big is 3I Atlas? Size estimates from Photometry. It's not easy to figure out 3I Atlas's size. Astronomers must use indirect techniques to analyze distant objects, unlike spacecraft that can directly photograph close asteroids or comets. The main method used to determine 3I Atlas's size is photometry, which measures how much sunlight it reflects. Scientists can determine its diameter by comparing its brightness with hypotheses regarding its reflectivity, or albedo. Initial measurements placed 3I Atlas as a relatively small object by planetary standards, but still significantly larger than some of its interstellar predecessors. Photometric data suggest that 3I Atlas has an effective size somewhere between 60 and 120 meters across, depending on its actual albedo. If it has a darker surface, coated with carbon-rich dust like many long-period comets, it would need to be larger to reflect the amount of light observed. If it is somewhat brighter, with fresher ice exposed, it could be closer to the smaller end of the size range. For comparison, Oumuamua, the first confirmed interstellar object, was estimated to be roughly 100 meters long, though its elongated shape made precise sizing difficult. Comet Borisov, on the other hand, was much larger, with a nucleus possibly over 1 kilometer wide. 3I Atlas fits neatly between these two, more comparable to Oumuamua in scale, but far more comet-like in appearance. Its estimated size also places it within the typical range for solar system comets, suggesting interstellar comets may be broadly similar in scale to those formed in our own system. 3I Atlas's rotating brightness varies, suggesting that it could not be a completely spherical entity. Rather, it could be lengthy or asymmetrical, like a piece of broken rock and ice that was forcibly thrown out of its home system. It could spin in a way that exposes various surface portions to sunlight, causing brightness to increase and decrease in repetitive patterns, according to fluctuations in the light curve. Because differing surface orientations may reflect more or less sunlight depending on the viewing angle, these changes complicate size estimates. The rarity of finding such intergalactic visitors can be explained by their comparatively tiny size. 3I Atlas was dim even at its brightest, and could only be seen for a short time with moderate to large telescopes. Given how easy such things may go undetected against the Milky Way's vast star field, it is impressive that Atlas was able to discover it before its closest approach. 3I Atlas might not have been seen at all if it had been half as large as it was thought to be. Its structural strength and survivability during the voyage are also affected by the predicted size. As they approach stars, objects this tiny are more susceptible to fragmentation. As demonstrated by some sun-grazing comets in our own system, tidal forces and solar heating have the power to fracture or even totally disturb frozen planets. 3I Atlas appears to have sufficient internal cohesiveness to tolerate mild gravitational and thermal stresses, as evidenced by its relative stability. Astronomers did observe subtle signs of outgassing, though, which suggests that the planet's surface ices were gradually sublimating as it warmed. Normal cometary behavior as opposed to cataclysmic breakdown. Its influence on interstellar population statistics models is another intriguing feature of its scale. Numerous ice shards of comparable sizes are probably scattered throughout the galaxy if 3I Atlas is an example of an interstellar comet. According to statistical estimates based on its discovery, as well as those of Oumuamua and Borisov, the Milky Way may contain billions of these objects, many of which were expelled from nascent planetary systems. Future sky scans will probably uncover many more, providing us with a greater understanding of their size distribution, even if the majority are too weak for us to observe. The origin of 3I Atlas is also called into doubt due to its tiny scale. Is it a piece of something much bigger, such as a broken exoplanet or a disturbed dwarf planet, or was it expelled whole as a single frozen body? Given its erratic light curve and perhaps extended form, it is more likely to be a planetary piece than a primordial comet. According to ejection models, collisions and gravitational slingshots can hurl large amounts of debris into interstellar space during chaotic planetary formation. Dust tail versus no tail, does it behave like a comet? When studying an interstellar visitor such as 3I Atlas, astronomers sometimes wonder if it acts more like an asteroid or a comet. Because it indicates the composition of the thing and the amount of volatile substance it contains, the difference is crucial. When comets' ices sublimate due to heat from the sun, they usually generate a coma, which is a luminous ring of gas and dust, and occasionally a tail. In contrast, asteroids are mostly dormant, reflecting sunlight and emitting no discernible gases. The solution for 3I Atlas is somewhere in the middle, making it difficult to distinguish between these two groups and posing queries about how interstellar objects change over the course of their protracted travels. When 3I Atlas was first detected, it showed faint signs of activity. Photometric observations revealed a diffuse halo surrounding its nucleus, indicating that some of its surface ices were sublimating as it approached the Sun. This coma was much weaker than what we saw with Comet Borisov, 2I Borisov, which displayed a spectacular classic cometary tail. But it was far more active than Oumuamua, 1I Oumuamua, which showed no visible coma at all. 3I Atlas, therefore, occupies a unique middle ground, active enough to confirm the presence of volatile ices, but subdued enough to suggest a surface that may be partially covered by insulating material. The activity appears to have been limited to a thin dust halo rather than a well-defined tail. Unlike Borisov, whose tail stretched tens of thousands of kilometers, 3I Atlas's dust production was faint and localized. This could mean several things about its composition and history. One possibility is that the object has been traveling through interstellar space for so long that its outer layers have become coated with organic rich crusts formed by cosmic radiation. These hardened crusts can seal off deeper ices, preventing them from easily escaping when warmed by the Sun. It's also possible that 3I Atlas contains less volatiles than other comets in the solar system. It may have been richer in silicate and stony material, with just thin layers of frozen gases left behind if it had formed closer to its parent star. In contrast to more volatile rich comets, which exhibit violent outgassing, these shallow ices generated the light coma we witnessed when they melted close to the Sun. To learn more about its behavior, astronomers closely examined the rates at which it produced dust. In comparison to Borisov, which ejected hundreds of kilograms of dust per second, 3I Atlas is estimated to have emitted just a few kilos of dust per second during its peak activity. The object never generated a dazzling sweeping tail that might be seen using modest telescopes, which can be explained by this feeble activity. However, because the departing gases included chemical traces of its internal makeup, even this little outgassing had scientific value. Spectroscopic observations of the faint coma detected water vapor, carbon monoxide, and possibly carbon dioxide, consistent with ices formed in the cold outer regions of a planetary system. The presence of carbon monoxide in particular suggests that it originated in an extremely cold environment, perhaps far beyond the equivalent of our Kuiper belt. This aligns with the idea that interstellar comets like 3I Atlas are ejected from the outermost regions of young planetary systems, where giant planets fling icy bodies into deep space. Additionally, the absence of a robust tail offers hints on the composition of its core. Solar heating may only penetrate shallowly into 3I Atlas's extremely porous or cracked core, causing gas to be released gradually rather than explosively. Its surface may have been changed by cosmic radiation and micrometeoroid impacts throughout millions of years of interstellar flight, forming a hardened covering that lessens the exposure of new ice. The question of whether various kinds of interstellar objects follow distinct evolutionary trajectories is also intriguingly raised by its limited activity in comparison to Borisov. Others, like 3I Atlas, may form insulating crusts that suppress their cometary activities, while others may stay comparatively clean, maintaining vast layers of frozen gases. By examining these variations, astronomers will be better able to comprehend the effects of interstellar travel on ice and if they can continue to function after spending millions of years floating between stars. The faint coma of 3I Atlas also has implications for theories about panspermia, the idea that life's building blocks could travel between star systems on comets. If objects like 3I Atlas still carry organic-rich material and volatile ices after eons in interstellar space, they could serve as natural carriers for complex molecules. Even faint outgassing indicates that such compounds can survive the harsh conditions of space and be released when these travelers pass close to a star. The diversity of these visits is demonstrated by contrasting 3I Atlas with the other two known interstellar objects. While Oumuamua was enigmatic, dormant, and perhaps covered in reflective metallic hydrogen or biological crusts, Borisov was practically a textbook comet, acting just like those in our solar system. In the middle is 3I Atlas, which is ice yet partially sealed by an ancient surface and active but not explosive. The notion that interstellar objects constitute a diversified population, formed by many birth contexts and billions of years of exposure to interstellar circumstances, is supported by their unusual behavior. Its rotation period, tumbling or stable spin. Understanding 3I Atlas's internal structure, surface activity, and even its interstellar history depends on its ability to rotate across space. This is more than simply a mechanical detail. Where and how gas and dust escape is determined by the way rotation regulates how sunlight heats the surface. While a chaotic tumble might expose volatile rich zones periodically, causing bursts of activity, a quick steady spin might spread heat uniformly. Astronomers may piece together how 3I Atlas formed, how long it has been traveling, and how much structural stress it has suffered by determining whether it is spinning smoothly or tumbling randomly. Astronomers measured its rotation by analyzing light curves, the small variations in brightness as the object turned in space. Just like a spinning potato reflects different amounts of sunlight as it rotates, 3I Atlas's brightness fluctuated in repeating patterns. These variations were subtle, indicating that its rotation period is not extremely fast, but they were clear enough to establish that the object is indeed rotating rather than locked in a static orientation. A rotating period of around 9 to 12 hours is suggested by preliminary data. However, this estimate is subject to uncertainty because of its faintness and erratic activity. This range is similar to that of numerous comets in the solar system, which often rotate for durations ranging from a few hours to a full day. 3I Atlas appears to be physically strong enough to withstand interstellar travel, without disintegrating due to its rather moderate spin, but not so rapid that centrifugal forces may potentially destroy it. However, the light curve also hinted at something more complex than a simple uniform spin. Its brightness changes did not follow a perfectly smooth sinusoidal pattern. Instead, they showed asymmetrical peaks, a possible sign of an elongated or irregular shape. This irregularity could mean that 3I Atlas is not rotating around a single stable axis, but might be in a tumbling state, what astronomers call a non-principal axis rotation. Tumbling is common in small bodies that have experienced gravitational or collisional disturbances, and for an interstellar object, it makes perfect sense. As 3I Atlas moved around the galaxy over millions of years, it probably felt minor gravitational pulls from stars that passed by, and even collisions with micrometeoroids. An object's spin may be progressively changed by these interactions, causing it to stop rotating steadily. Its patchy coma and dust release might also be explained by tumbling. Confined volatiles may sublimate irregularly rather than uniformly when various areas are exposed to sunlight at random. The structural strength of 3I Atlas may also be shown if it is tumbling. A human may experience stress from tumbling, and delicate things frequently shatter when their spins become unsteady. 3I Atlas's ability to bear the torque from any erratic rotation is suggested by the fact that it has sufficient internal cohesion, perhaps kept together by a mixture of ice and compressed dust. The rotation period also gives clues about how active it might have been before entering our solar system. A long interstellar journey exposes objects to torques from outgassing each time they pass near a star. Even small amounts of sublimation, when repeated over multiple stellar flybys, can slowly alter rotation, sometimes spinning objects up to the point of breakup. 3I Atlas's moderate spin rate implies it hasn't been excessively spun up, suggesting either that it has only passed close to a few stars during its lifetime, or that its insulating surface crust has kept its outgassing relatively subdued. The possibility of tumbling begs the question, was its expulsion from its home star system the reason for its erratic spin? Giant planets frequently behave as gravitational slingshots during planetary formation, forcefully hurling smaller debris into interstellar space. 3I Atlas could have been thrown for millions of years by the torque from a near collision with a huge planet. If this is accurate, its spin may serve as a fossil record of the precise occasion that set it out on its cosmic adventure. Comparing its rotation to other interstellar objects further emphasizes its uniqueness. Oumuamua showed clear evidence of tumbling, with brightness variations that suggested an extremely elongated cigar-like shape. Borisov, on the other hand, spun in a more typical stable manner, much like a solar system comet. 3I Atlas once again falls between these two extremes. Its moderate but possibly unstable rotation reinforces the idea that interstellar objects form a diverse population, with different evolutionary paths. Chemical clues, spectroscopic analysis of its composition. Spectroscopy, or the study of how an object reflects and emits light, is one of the most useful methods astronomers employ to comprehend objects like 3I Atlas. Scientists can identify the atoms and chemicals present by examining the wavelengths of sunlight that reflect off its surface and pass through its coma. This information is essential for an interstellar object, as it gives a direct chemical fingerprint of a world that was generated orbiting another star. Observations of 3I Atlas's spectrum revealed that it shares many characteristics with typical solar system comets, suggesting that the processes that form comets may be universal across planetary systems. The most prominent signature was that of water ice, confirmed through faint absorption features in the near-infrared spectrum. This is unsurprising, as water is one of the most common substances in both the solar system and interstellar comets. Its presence indicates that 3I Atlas formed in a cold outer region of its home system, far from its parent star. Alongside water, astronomers detected volatile gases such as carbon monoxide, CO, and carbon dioxide, CO2, both common in solar system comets but present in varying ratios depending on their formation environment. 3I Atlas showed a slightly higher proportion of carbon monoxide relative to water than most Kuiper Belt comets, suggesting it may have formed in a colder, more distant region of its system than our local comets typically do. This difference provides hints about the conditions of its birth star, possibly a cooler or dimmer star, where icy bodies form farther out than in sun-like systems. Additionally, spectroscopy suggested the existence of more complex chemicals, maybe organic compounds and hydrocarbons. These show up as faint bands of absorption in the ultraviolet and near-infrared, suggesting that some of its surface ices may have been converted into complex organics by cosmic ray bombardment during its lengthy interstellar journey. This is comparable to the way that radiation progressively darkens and reddens the surfaces of long-period comets and trans-Neptunian objects in our own solar system. The finding of organics is especially significant because it supports the hypothesis that primordial chemistry may be transported throughout the galaxy by interstellar debris. These complex chemicals are carried into space by the gas and dust released by 3I Atlas, despite its weak activity, and may eventually fall on planets in neighboring systems. Numerous items similar to it might aid in the distribution of life's chemical components across the Milky Way over billions of years. The spectroscopic data also provide clues about how pristine its material is. Some interstellar objects, like Borisov, displayed chemical signatures nearly identical to solar system comets, suggesting that their material hasn't changed much since formation. 3I Atlas, however, shows slightly processed surface layers. The combination of fresh ices and radiation-darkened organics suggests that while its core remains mostly untouched, its surface has been altered by millions of years of cosmic exposure. This layered structure, a weathered outer crust shielding fresh ice beneath, is exactly what scientists expect from interstellar travelers. The detection of silicate dust in its coma further supports the idea that it formed in a protoplanetary disk much like our own. Silicates, which show up as infrared emission peaks, are rocky materials that condense in warmer regions closer to a star. Their presence in 3I Atlas's dust implies that the object may be a mixture of icy and rocky material, possibly formed in a transitional zone between a system's inner rocky region and outer icy belt. This strengthens theories that many interstellar objects are ejected during the chaotic mixing of these regions in young planetary systems. The composition's seeming banality is among its more unexpected features. Despite minor variations in gas ratios and radiation processing level, 3I Atlas doesn't seem to include any unusual or unidentified ingredients. This implies that the chemical circumstances under which planetary systems arise may be mostly identical throughout the galaxy. It suggests that the building blocks for planets, and even life, are widespread across the Milky Way if comets from a different star system resemble our own in appearance and behavior. Comparing 3I Atlas to Oumuamua and Borisov, what's different? Comparisons with the first two, 1I Oumuamua and 2I Borisov, are crucial to comprehending the diversity of these galactic nomads. The discovery of 3I Atlas was just the third time scientists had the opportunity to examine an interstellar object up close. Because of its creation environment, ejection history, and time spent wandering across interstellar space, each one has a distinct narrative to tell. Scientists may start to get a more comprehensive understanding of the types of materials produced by other planetary systems and the evolution of these extraterrestrial objects by analyzing how 3I Atlas varies from its predecessors. Activity and appearance are where the differences are most noticeable. With a luminous coma and a lengthy tail that behaved nearly precisely like comets in our own solar system, Borisov was clearly a comet. Its composition clearly suggested that comet formation processes are similar across the galaxy, since it closely matched that of typical ice bodies created in the outer regions of planetary systems. However, Oumuamua showed no signs of a coma or tail at all, instead resembling a dry asteroid or a deeply worn rock with surface volatiles locked behind a crust. 3I Atlas falls between these two extremes. It showed faint cometary activity, an indicator of some remaining volatile ices, but far weaker than Borisov's. Its thin halo of gas and dust barely registered compared to Borisov's vigorous outgassing, suggesting that much of its surface is insulated by a hardened crust formed during its long interstellar journey. However, it was not entirely inert like Oumuamua. The detection of water vapor and carbon monoxide confirmed that at least some of its interior still contained active, pristine ices. The differences in surface chemistry also provide key insights. Borisov's chemical composition was remarkably similar to solar system comets, dominated by water ice, carbon monoxide, and carbon dioxide in familiar ratios. Oumuamua's lack of activity made direct spectroscopic analysis difficult, but its reddish hue implied a surface coated in organic-rich material processed by cosmic rays over millions of years. 3I Atlas shares elements of both. Its spectrum revealed a mix of water ice, carbon monoxide, and possibly complex hydrocarbons, suggesting it formed in a cold outer disk but has been significantly altered by interstellar weathering. Among the three, Oumuamua is the most peculiar in terms of form and rotation. Discussions over whether it was a man-made probe, a hydrogen iceberg, or a piece of a disturbed planetessimal were sparked by its tumbling spin and long cigar-like or perhaps pancake-like form. Borisov, on the other hand, was nearly textbook normal. Like other active comets, it had a spherical nucleus with a steady spin. Once more, 3I Atlas occupies the center. Though not quite as severe as Oumuamua's erratic spinning, its light curve points to an unusual, potentially elongated form with signs of tumbling. This might suggest that despite intense gravitational interactions during ejection, it has maintained enough structural stability to prevent disintegration. Size estimates also highlight diversity. Borisov was the largest of the three, with a nucleus likely over 1 kilometer across, making it easily visible through amateur telescopes. Oumuamua was far smaller, estimated at around 100 meters long, and would have gone unnoticed without modern surveys. 3I Atlas measures between 60 and 120 meters in diameter, closer to Oumuamua's size, but active enough to be classified as a weak comet. Its relatively small size also explains why it was harder to detect and why its period of visibility was short. The differences in activity levels might reflect not just composition, but also age and travel history. Borisov, with its abundant volatiles, may have been ejected more recently, spending less time exposed to cosmic radiation. Oumuamua's lack of activity suggests it may have spent much longer in interstellar space, developing a thick radiation-processed crust that sealed off its ices. 3I Atlas appears to have an intermediate age. Its faint activity implies some interstellar weathering, but not complete surface sealing. Formation environments are also clarified by these similarities. Borisov most likely formed in a system like ours, where frozen bodies formed in a frigid outer disk beyond big planets. Although the precise origin of Oumuamua is still unknown, its dry, processed surface suggests that it either have been a piece of a bigger planetary body or have originated in a warmer interior area. The high carbon monoxide concentration of 3I Atlas points to an extremely cold formation environment, maybe surrounding a dimmer star where volatile ices might condense further out. Could it be a planetary fragment? The possibility that 3I Atlas is not a normal comet at all is among the most fascinating ideas. Rather, it may be a piece of a bigger planet, a shard of ice and rock that was forcefully ripped from its mother planet and thrown into interstellar space. Although speculative, this theory is backed by a number of indicators related to its size, shape, and chemical composition, none of which quite fit the characteristics of a typical long-period comet. If accurate, 3I Atlas would provide us with a unique chance to examine material from deep within a different planetary system, material that may have formerly been a moon or possibly the crust of an extraterrestrial planet. The idea that interstellar space could be filled with planetary debris isn't far-fetched. Planetary formation is a chaotic process. In young star systems, newly formed planets and moons frequently collide as they jockey for stable orbits. These violent impacts can shatter worlds, scattering fragments across their systems. In addition, massive gas giants often act as gravitational slingshots, ejecting huge amounts of rocky and icy material into interstellar space. Simulations suggest that for every planet that successfully forms, countless smaller bodies are flung out during the system's early evolution. Over billions of years, this process could seed the galaxy with trillions of wandering fragments. For 3I Atlas, several characteristics raise the possibility of a planetary fragment origin. First, its light curve variation chint at an elongated, irregular shape, similar to fractured debris rather than the rounded, roughly spherical nuclei of most comets. Its brightness fluctuates as it spins, suggesting large surface irregularities or jagged edges, typical of a body that broke apart rather than forming gently in a protoplanetary disk. Second, its spectroscopic composition shows a mix of volatile ices and silicate dust, implying it may not be a pristine comet nucleus. Instead, it might be a chunk of a differentiated body, a planetessimal or moon whose interior layers were once separated into rocky and icy components. If it were ripped from a larger body during a catastrophic collision, it could carry both rocky material from the crust or mantle and ices from deeper layers. This would explain why it shows weaker activity than Borisov. If much of its icy material is buried beneath rocky or processed layers, less of it would sublimate when heated by the sun. This notion is further supported by its black, organic-rich surface and modest albedo. Any interstellar object's surface can be weathered by cosmic radiation over millions of years, but a planetary fragment would have likely begun with a more complicated mixture of volatiles and minerals than a normal comet. The black crust we see today may have formed as a result of these minerals reacting over time to cosmic ray bombardment. Comparisons to Oumuamua further strengthen the idea. Oumuamua's lack of visible activity and unusual elongated shape led some scientists to propose it too could be a fragment of a disrupted planetessimal, possibly torn apart by tidal forces near its parent star. 3I Atlas, though more comet-like, shares some of these characteristics, sitting somewhere between Borisov's pristine cometary behavior and Oumuamua's inactive, fractured appearance. If 3I Atlas is indeed a planetary fragment, it would have been ejected under far more violent circumstances than typical cometary bodies. While comets are usually pushed out of their systems gradually by gravitational interactions, a planetary fragment might have been launched during a catastrophic event, such as a giant planet migrating inward and scattering inner rocky worlds, or a close stellar flyby destabilizing an entire system. These scenarios are not rare in young star systems, and many exoplanet studies suggest that massive orbital disruptions are common during planetary formation. Determining if 3I Atlas is a planetary fragment has significant ramifications for exoplanetary science and is not only an academic curiosity. Interstellar objects are basically free samples of other worlds if they can be verified as planetary detritus. Analyzing their chemistry may provide knowledge about the interiors of extraterrestrial worlds that is currently unattainable. It may indicate distinct planetary formation processes around other stars if the mineral and ice composition of 3I Atlas is substantially different from that of solar system bodies. Its potential as planetary debris also raises questions about whether such fragments could carry prebiotic or even biological material between star systems. While the odds of life surviving interstellar travel are slim, large rocky fragments could, in theory, shield organic molecules from radiation for millions of years. If even one such fragment landed on a young habitable planet, it might help seed the basic ingredients for life, a concept linked to Panspermia theories. Naturally, it is challenging to determine whether 3I Atlas is a planetary fragment. The majority of our results are based on indirect observations because we do not have direct samples. However, this concept remains up for debate because of its form, diverse content, and minimal activity. Patterns showing the prevalence of planetary pieces relative to typical cometary guests may show up when we find additional interstellar objects. Why is it so rare to spot interstellar objects? It may appear unexpected at first that there have only ever been 3 verified interstellar objects discovered: Oumuamua, Borisov, and now 3I Atlas. Shouldn't we be seeing these visitors all the time if planetary systems around the galaxy are continuously ejecting comets, asteroids, and debris into space? Although it is extremely difficult to detect them, interstellar objects are really rather common throughout the galaxy. Their small size, faintness, and amazing speed are more likely to be the reason for their rarity in our observations than their real population in interstellar space. The first reason is sheer size and brightness. Interstellar objects tend to be relatively small, often only tens or hundreds of meters across, like 3I Atlas. They are far smaller than most planets or even large asteroids, which means they reflect very little sunlight. Their dark radiation process surfaces further reduce their brightness. Many, like 3I Atlas, have albedos as low as 4–10%, making them as dark as charcoal. Unless they pass very close to Earth or develop a bright cometary tail, they remain practically invisible against the star-filled backdrop of the night sky. The second major challenge is speed. Interstellar objects move far faster than typical solar system comets or asteroids. Traveling at tens of kilometers per second, they whip through the inner solar system in a matter of months. By the time they are close enough to detect, they are often already on their way out, leaving astronomers with only a short observation window. For example, Oumuamua was detected only after it had already passed its closest approach to the Sun, giving scientists just weeks to study it before it faded from view. The third factor is sky coverage. Until recently, we simply weren't looking hard enough or often enough to catch these faint, fast-moving objects. Most astronomical surveys were designed to track bright planets, stars, and galaxies, not small, dim points of light darting through the solar system. Even specialized surveys for near-Earth objects like Atlas only scan portions of the sky at a time, leaving vast areas unmonitored on any given night. The odds of spotting a tiny, fast-moving interstellar object against billions of stars are incredibly slim. Furthermore, interstellar objects are significantly more difficult to detect since they spend the majority of their time distant from the Sun. Only as they get closer to the inner solar system and sunlight starts to warm their surfaces, do objects like 3I Atlas become bright enough to see. This brightening may never occur for things that are dormant, or rather weakly active. For example, since it lacked a tail to reflect additional light, Oumuamua remained dim even close to perihelion. If they hadn't gotten intelligent enough to notice, countless additional interplanetary visitors may have gone through unnoticed. Population models suggest that despite these detection challenges, interstellar objects are extremely common. Astronomers estimate that for every star in the Milky Way, trillions of icy and rocky fragments may drift freely through interstellar space. Most were ejected billions of years ago during the chaotic early stages of planetary formation. Our own solar system likely ejected huge numbers of comets and asteroids into interstellar space as Jupiter and Saturn migrated in their orbits, and other star systems are thought to have done the same. The galaxy may be teeming with these wanderers. We just can't see most of them. The advancements in detecting technology are demonstrated by the fact that we have discovered 3 interstellar objects in just over 6 years. The game has been altered by surveys like ATLAS and PanSTARRS, which scan the sky every night and highlight any objects that move erratically quickly or in unexpected directions. This will be further pushed by the forthcoming Legacy Survey of Space and Time, LSST, at the Vera Rubin Observatory. It is anticipated that LSST will discover dozens or possibly hundreds of interstellar objects every decade because of its enormous mirror and quick, wide-field photography, significantly increasing our sample size. However, the number of those we can locate is limited. Many interstellar objects will pass far from Earth, where even LSST won't be able to detect them, and the majority are probably merely tens of meters wide, far smaller than 3I Atlas. Most will be undetectable, moving silently and undetected through the solar system. Brightness variations, signs of an irregular shape. The way a distant object's brightness varies over time is one of the first indicators astronomers use to deduce its physical makeup. These variations in brightness, which are shown as light curves, imply that 3I Atlas is an unevenly shaped, perhaps elongated piece rather than a smooth spherical mass. Different surface portions are exposed to sunlight with each revolution, resulting in patterns of rising and falling reflected light that show the object's form and spin behavior. The light curves of 3I Atlas show noticeable but modest variations in brightness, repeating every 9 to 12 hours, which is consistent with its estimated rotation period. The fluctuations are not extreme, indicating it is not as dramatically elongated as Oumuamua, whose brightness varied by a factor of up to 10 due to its extreme cigar or pancake-like shape. However, the irregularity of 3I Atlas's brightness peaks suggests that it may still have a lumpy, uneven surface, with large ridges, depressions, or possibly a fractured structure. An irregular shape fits well with what we know about interstellar objects. Unlike large planets and moons, which are shaped into spheres by gravity, small icy and rocky bodies are often irregular, especially if they are fragments of larger objects. Ejection events, gravitational slingshots, planetary collisions, or tidal disruptions can shatter planetesimals, creating jagged shards that drift through space. The uneven surface of 3I Atlas might therefore be evidence of a violent past, possibly tied to its ejection from its home star system. Its brightness variation's amplitude also suggests how reflective its surface could be. The light curve would be exaggerated by the disparity in albedo if one side was covered with dark, radiation-processed material and the other with new, brilliant ice. A mixed surface with new volatiles under a worn crust is already suggested by spectroscopic evidence. The irregular patterns of brightness may be caused by this patchy surface. The fact that the brightness variation is moderate rather than extreme may indicate that 3I Atlas has undergone some degree of rounding over time. Over millions of years, collisions with micrometeoroids and sublimation of exposed ices can erode sharp edges, making the object less jagged than when it was first ejected. However, its shape is still far from smooth, meaning it has not been significantly reshaped by processes like melting or internal geological activity, consistent with a small, inactive interstellar traveler. Its distinct location is supported by comparisons to other interstellar objects. Oumuamua's unusual elongation raised the possibility that it was a piece of a bigger, broken body, or possibly a sheet of material that had collapsed like a hydrogen iceberg. In contrast, Borisov had a fairly spherical nucleus and no change in brightness, making it far more typical of comets in the solar system. The 3I Atlas, which appears to be a piece of a bigger ice body rather than a pure comet nucleus, is situated between them. It is irregular, but not strange. The shape also affects how it responds to sunlight. Irregular bodies heat unevenly, which can drive localized activity. If certain areas are covered in insulating crust, while others expose fresh ice, gas jets may erupt from only a few active spots, further altering the object's rotation over time. These jets can create small torques, slowly changing the spin rate or causing slight wobbles, which may account for the subtle irregularities in 3I Atlas's light curve. Whether its uneven form makes it more brittle is another consideration. Compared to spherical bodies, jagged pieces frequently have less structural stability. 3I Atlas may disintegrate more readily than a solid monolithic core if it passes too near a star or encounters powerful tidal forces. Its longevity during its journey through our solar system indicates that, despite its irregularity, it is cohesive and compact enough to tolerate a small amount of gravitational and heat stress. Astronomers continue to refine its shape models by combining photometric data with rotation period measurements, but the faintness of 3I Atlas limits how much detail can be extracted. Future telescopes with higher sensitivity, like the Vera Rubin Observatory, may allow for more precise shape modeling of such interstellar objects, giving clearer pictures of their structures. What star system could have ejected it? Candidate origins. Finding 3I Atlas's precise birthplace is one of the hardest things in interplanetary astronomy. After being expelled from its home system, an item drifts for millions or perhaps billions of years as the Milky Way's gravitational field, passing stars, and massive molecular clouds continuously shove it in that direction. Astronomers can still identify possible origin areas by carefully retracing its hyperbolic orbit, which can reveal information about the kind of star system that sent it into interstellar space. When 3I Atlas was first detected, astronomers calculated its incoming direction relative to the solar system. Its path appears to point roughly toward regions of the sky near the constellations Carina and Scorpius, both of which are rich in stellar nurseries, massive regions of gas and dust where new stars and planetary systems are born. These star-forming regions are prime candidates because the chaotic gravitational interactions in young planetary systems frequently eject comets, planetesimals, and even planetary fragments into interstellar space. A young, sun-like star with massive planets is one kind of system that may have expelled 3I Atlas. Large gas giants move across the protoplanetary disk in these systems, dispersing smaller rocky and ice bodies in the process. Some of these smaller objects are sent forth with escape velocity, while more are hurled smashing into the star or planets. These expelled particles eventually transform into 3I Atlas and other interstellar nomads. This theory is supported by its chemical composition, which includes carbon monoxide and water ice, which normally occur in the colder outer regions of such planetary systems. A red dwarf system is an additional contender. The most prevalent stars in the Milky Way are red dwarfs, several of which are known to contain thick ice belts. Red dwarfs' ice and habitable zones are located significantly closer in because they are colder and fainter than stars like the Sun. Ice bodies might readily be sent into interstellar space by ejection events brought on by migratory planets or close star interactions. 3I Atlas's comparatively high carbon monoxide level indicates that it formed in a colder atmosphere, which is consistent with a system around a cooler star. Tracing its path back to a specific star, however, is extremely difficult. The Milky Way is constantly moving and reshaping itself. Stars orbit the galactic center at different speeds, and over tens of millions of years, their relative positions change dramatically. By the time 3I Atlas reached our solar system, its trajectory had likely been altered by numerous gravitational encounters, making precise backtracking nearly impossible. Even if its incoming direction points generally toward Carina or Scorpius, the star or stars that ejected it may no longer be anywhere near that region today. By comparing its journey to the locations and movements of neighboring stars recorded by missions such as Gaia, which records billions of stars with remarkable accuracy, some researchers try to simulate potential interactions. Astronomers can find stars that might have passed close to 3I Atlas's predicted course millions of years ago by running simulations backward in time. But the further back these models extend, the less definite they get. And to date, no one star has been conclusively pinpointed as its genesis. The ejection mechanism also influences where it likely came from. Most interstellar objects are thought to be thrown out during the early chaotic phases of planetary system formation, typically within the first 100 million years of a system's life. If 3I Atlas formed in a young, dense cluster of stars, gravitational interactions between nearby stars could have increased the odds of ejection. Star clusters often experience close stellar flybys that destabilize planetary systems, launching comets and fragments into interstellar space. If it came from such an environment, 3I Atlas could have been ejected relatively early and spent tens of millions of years drifting before reaching us. Its age as an interplanetary voyager is also hinted at by its surface processing. Long-term exposure to cosmic rays, which progressively change the chemistry of the surface, is suggested by the crust's black, organic-rich composition. Brighter, fresher surfaces are often retained by objects that have traveled for a few million years, whereas those that have strayed for tens or hundreds of millions of years have deeper radiation processing. This lends credence to the theory that 3I Atlas was expelled a long time ago, maybe at the inception of its home system. Could it have carried organic molecules from another system? Whether 3I Atlas contains organic molecules, the fundamental chemical components of life, is one of the most intriguing mysteries surrounding the spacecraft. Complex carbon-based compounds found in interstellar objects like 3I Atlas may be crucial in dispersing prebiotic chemistry throughout the galaxy, supporting theories such as Panspermia, which postulates that the components of life move between star systems on natural carriers like comets and asteroids. Spectroscopic analysis of 3I Atlas strongly suggests that it does indeed harbor organic compounds. Its faint greenish coma hints at the presence of cyanogen, Cn, and diatomic carbon, C2, two carbon-rich molecules commonly found in active comets. These gases are formed when sunlight breaks down larger organic compounds on the surface, meaning 3I Atlas likely has a layer of complex carbon molecules coating its nucleus. Similar organics have been found on comets in our solar system and are considered key precursors to amino acids, nucleobases, and other molecules necessary for life. The surface of 3I Atlas is also dark and low in reflectivity, with an albedo of roughly 4 to 10%. This dark coloration is typical of comets coated in tholins, complex organic solids produced when ultraviolet radiation and cosmic rays interact with simple ices like methane and nitrogen. Over millions of years drifting through interstellar space, 3I Atlas would have been bombarded by high-energy radiation, creating thick layers of these reddish-brown organics. While this crust may insulate the ices beneath, it also preserves a chemical record of the processes that shaped it during its long voyage. These discoveries are significant because they demonstrate that organic chemistry is not exclusive to our solar system. Prebiotic chemistry may be a typical galactic phenomenon if 3I Atlas originated around another star and produced the same kinds of complex organics as our nearby comets. Ice grains covered in biological materials may frequently occur in the outer parts of protoplanetary disks in planetary nurseries across the Milky Way. These ices eventually coalesce into comets and planetesimals, which can subsequently provide nascent planets with organic-rich material. The interior of 3I Atlas is likely even more pristine than its processed surface. The cosmic ray-hardened outer shell may be only a few meters thick, shielding the inner layers of ice from radiation. Deep inside, untouched ices could contain a chemical mix identical to what existed when it first formed around its parent star. These preserved ices may include more fragile molecules such as methanol, formaldehyde, and even simple amino acid precursors. If someday we could sample material directly from its core, we might find a frozen snapshot of the chemistry that existed in another star system billions of years ago. This brings up the captivating concept that things like 3I Atlas serve as extraterrestrial messengers of the elements necessary for life. Some of their ice and dust may escape into space when they approach stars, propelled by the pressure of solar radiation. These tiny, organic-rich particles can wander for millions of years before hitting a planet in a different system. Experiments have demonstrated that many organic molecules may withstand extended exposure to cosmic radiation if protected by rock or ice, despite the severe nature of the voyage. The chemical seeds required for life most likely can survive intergalactic travel, even if life itself cannot. The 3I Atlas also backs up the idea that matter often moves between star systems. Its very existence is evidence that billions of comets, fragments, and planetesimals are periodically ejected into the galaxy by planetary systems. If even a tiny portion of them are rich in organic matter, the galaxy may be continuously exchanging the elements necessary for life between stars, increasing the likelihood that life will arise wherever the circumstances are favorable. Gravitational interactions on its way in. Which planets nudged it? The gravitational attraction of the large planets, particularly Jupiter and Saturn, has had a subtle impact on 3I Atlas's trajectory across our solar system, which is not a straight line. The hyperbolic course of 3I Atlas was predetermined when it entered the solar system, but passing objects' orbits can be changed in a special fashion by the gravity of our massive planets. By slightly altering the object's speed and orientation, these gravitational interactions can provide important details about its trajectory through space and the forces that influenced it. When 3I Atlas was first detected by the Atlas survey, astronomers calculated its incoming velocity and trajectory. As soon as it was clear that the object was interstellar, astronomers began to track its passage through the solar system, paying close attention to any changes in its path that might be caused by the gravity of planets it encountered. Unlike a standard comet or asteroid, which orbits the Sun in a predictable elliptical or circular path, 3I Atlas was moving at such high speeds that it was not bound by the Sun's gravity. Its hyperbolic trajectory suggested it was simply passing through, but that didn't mean it wouldn't be influenced by the solar system's massive planets. Jupiter, the largest planet in our solar system, is known for its gravitational slingshot effect, which can redirect objects with incredible precision. This gas giant has an outsized influence on objects passing through the inner solar system. Its immense mass allows it to gravitationally deflect asteroids, comets, and other objects, sending them on new trajectories. For 3I Atlas, passing near Jupiter would have caused a slight change in its velocity and direction, nudging it further into the solar system. Nonetheless, 3I Atlas's trajectory indicates that, in comparison to things that approach the gas giant far more closely, Jupiter's impact on the object's course was probably negligible. The massive planet's gravity would have been sufficient to make little corrections, even though it was traveling in an exaggerated manner. 3I Atlas's gravitational collision probably only resulted in a minor deflection, only enough to significantly alter its path through the solar system. Because its perihelion, its closest approach to the Sun, was still fairly distant from Jupiter. On the other hand, Saturn, with its proximity to 3I Atlas's path, may have had a more noticeable influence. While 3I Atlas's trajectory kept it far from both Jupiter and Saturn, Saturn's gravity could still have affected its orbit as it passed through the outer regions of the solar system. Much like Jupiter, Saturn has a huge mass, and its gravitational field extends far into space. The planet's gravity may have influenced 3I Atlas's hyperbolic trajectory, adding to the minor alterations caused by Jupiter. In fact, the small changes in the object's speed and trajectory over time suggest a subtle but significant gravitational effect by one of the gas giants. The speed and trajectory of 3I Atlas, however, stayed surprisingly consistent with what would be anticipated of an interstellar object in spite of these gravitational interactions. The object's hyperbolic orbit remained unaltered despite Jupiter and Saturn's gentle prods, suggesting that it was not attached to the Sun and would continue its voyage across space without being discovered by the solar system. This highlights the object's interstellar nature and demonstrates how little the Sun and its planets affected the object's overall journey. The way the gas giants interact with each other also makes us wonder how many additional things from beyond the solar system go through it without being seen. Although the Atlas survey was lucky to find 3I Atlas, its tiny size and weak activity indicate that such objects are probably more frequent than we think. There could be dozens of interstellar objects, too weak to be detected with current technology, moving through the solar system at amazing speeds for every interstellar object, like 3I Atlas. These items may be deflected in unforeseen ways if they were caught by the gravity of a massive planet like Jupiter, adding to the chaotic and dynamic nature of interstellar object motions. Does it pose any threat? Minimum approach, distance calculations. As soon as scientists learned that 3I Atlas came from another planet and was moving very fast, they asked themselves if it could be a threat to Earth. Fortunately, the answer is no. 3I Atlas is traveling through the solar system at such high speeds that it will never get near to Earth, much like other interstellar objects. To understand how things like 3I Atlas interact with our solar system, and if future interstellar travelers may be dangerous, however, the minimum approach distance and trajectory calculations remain essential. 3I Atlas's hyperbolic trajectory means it is not bound to the Sun's gravity, and its path is a one-time visit. Even at its closest approach to the Sun, 3I Atlas never came near the inner solar system. Its perihelion, the point at which it was closest to the Sun, was approximately 0.3 astronomical units, AU, or about 45 million kilometers, which is still far beyond Earth's distance from the Sun of 1 AU. To put it into perspective, 0.3 AU is about the same distance as Mercury's orbit around the Sun. At this distance, 3I Atlas passed through the solar system with minimal risk of impacting any planet or celestial body. Even if it had been on a slightly different course, the sheer speed at which it was traveling, up to 60 kilometers per second at its closest approach, meant that it would have quickly moved past any planet without a chance of gravitational capture. Its speed alone ensures that it could not have been drawn into a stable orbit around the Sun or Earth, and thus the likelihood of a collision is practically zero. Determining the approach distance is essential for both planetary defense and comprehending the dynamic behavior of solar system interstellar objects. 3I Atlas belongs to a special type of objects that require careful investigation because of its extraordinarily high velocity, which is around 10 times that of regular comets. The possibility of other, larger interstellar objects passing closer in the future is still of curiosity, despite the fact that its close flyby was still distant from Earth. We might be able to follow more of these fast-moving spacecraft and make more accurate predictions about their routes as interstellar detection technology advances. For 3I Atlas, astronomers also made sure to assess minimum approach distances for other planetary bodies in the solar system. While it passed at a safe distance from Earth, 3I Atlas came closer to Jupiter and Saturn, two of the solar system's gas giants, which exert strong gravitational forces. The gravitational tugs of these massive planets are one of the reasons 3I Atlas's trajectory was slightly altered during its passage, although these nudges were not large enough to change its overall path significantly. While these interactions didn't pose any direct risk to the solar system, understanding how such gravitational interactions affect objects like 3I Atlas helps refine our models for predicting future interstellar visitors. Understanding how interstellar objects change over time also depends on figuring out the minimum approach distance. Although there is no chance of a collision with 3I Atlas as it passes by, the object's high speed and one-time track raise significant concerns about how future interstellar objects may behave. For instance, even though 3I Atlas will soon be beyond our grasp, its journey through the solar system offers important lessons about how we may watch and observe objects of a similar nature that might eventually approach Earth. The absence of any collision risk doesn't mean that astronomers aren't paying attention, though. Even with 3I Atlas safely passing through, its very presence in the solar system is a reminder that the universe is filled with fast-moving, high-speed objects. With advancements in interstellar object detection, such as the Vera C. Rubin Observatory and other next-generation sky surveys, we can identify such objects much earlier in their journey, giving us the necessary time to study them. At this point, 3I Atlas is a rare object, but as our technology for finding visitors from other stars improves, we may find more objects like it. Its origin and safe passage across interstellar space demonstrate that, despite their potential lack of imminent danger, interstellar objects remain intriguing and significant research topics. How long will it stay visible? The brief window of study. One of the most interesting and annoying things about studying 3I Atlas is how short its window of vision is. Interstellar objects like 3I Atlas are only visible to us for a brief period of time, in contrast to things that stay in our solar system for years or decades. As they continue their voyage out into the galaxy after passing through the inner solar system, their exaggerated trajectories guarantee that they will never be seen again. Astronomers face a special challenge during this short observation time, as they must move quickly to collect as much data as they can before these objects vanish into thin air. When 3I Atlas was first detected by the Atlas survey in December 2019, it was already moving at incredible speeds, and astronomers realized that its visit to the solar system was a once-in-a-lifetime event. Within just a few months, it would pass through its closest approach to the Sun and be on its way out, leaving our solar system behind. Unlike other comets that might return after a long period, 3I Atlas was on a one-way trip, and the window to study it was shrinking by the day. At the time of its discovery, 3I Atlas was still hundreds of millions of kilometers from the Sun. As it drew nearer, its brightness increased, but its visibility peaked just before perihelion, the closest point to the Sun. Once it passed perihelion in May 2020, its light began to fade, as expected for objects with limited outgassing. The solar radiation began to wear down its coma, and the dust and gases that created the faint halo around the object dissipated. The time to study it was short, but this made each observation more valuable. Due to its fast speed, 3I Atlas was only visible from Earth for a few months, giving astronomers a limited time to examine its activity. Because of this limited sight window, telescopes must coordinate their efforts in a time-sensitive manner to gather as much information as they can while the object is still within range. It was the focus of most big observatories, but only those with the most sensitive equipment could make accurate observations because of its faintness. When the Vera C. Rubin Observatory is online, it will be an important instrument for early detection of such objects. But when 3I Atlas was originally discovered, its time in the limelight was almost over. The short visibility period for 3I Atlas is a reminder of the challenges in observing interstellar objects. These objects travel so quickly and so far that their time within the solar system is brief. In the case of 3I Atlas, astronomers had only a matter of months from its discovery to gather data on its trajectory, composition, and activity. After its perihelion, its brightness faded rapidly, and it began to move out of view, leaving observers with limited opportunities to continue their research. For objects like this, time is of the essence, and every second counts. This makes it harder to protect the Earth as well. Since interstellar objects like 3I Atlas travel so quickly, there is very little chance of a collision, which makes their detection essential for tracking the cosmic environment. However, our ability to forecast future hazards improves with our understanding of the behavior of these objects and their frequency of passage through the solar system. Advances in early warning systems and detecting technologies are essential since these items are so elusive and challenging to capture in time. Astronomers will be able to identify these objects sooner and follow their travels more precisely in the future as surveys like the LSST and ATLAS continue to scan the sky with ever-increasing accuracy, allowing us more time to study them before they disappear. The fact that 3I Atlas was only visible for a short time further shows how temporary scientific discoveries are when it comes to interplanetary objects. Seeing the chemical, physical, and orbital properties of something that originated far outside of our solar system is a once-in-a-lifetime opportunity. We are gathering priceless information as we continue to study 3I Atlas that will help us better understand the origins of objects like it, including what types of star systems give rise to these travelers, how they change over the course of their lengthy journeys, and what information their compositions can provide about the chemistry of other planetary systems. What does its dust behavior reveal about alien comets? Finding out how the dust in 3I Atlas behaves tells us a lot about the nature of comets that are not a part of our solar system. In our solar system, comets are known for the dust tails that stick out from their surfaces when the sun's rays warm them up and cause melting. This process gives off gas and dust, which can leave a trail that goes for a very long way. 3I Atlas did some comet-like things, but its dust behavior was very weak and shaky. This made us wonder more about the nature of comets in the interstellar medium and how they are different from comets in our own solar system. Unlike Comet Borisov, which displayed an active and clearly visible tail as it passed through our solar system, 3I Atlas exhibited only a faint dust halo, barely visible even through large telescopes. This minimal dust activity has been a subject of great interest, as it suggests that interstellar comets may behave very differently than those native to our solar system. Instead of the large, bright comas and tails that typically define comets, 3I Atlas's dust behavior raises the possibility that the material it is made of is either more resilient to sublimation or that its volatile compounds are less abundant compared to solar system comets. The dust halo around 3I Atlas shows that it is outgassing, although its outflow of dust was not as strong as the tails of comets, which means that its surface probably doesn't have a lot of volatile material. This might mean that the object has been exposed to cosmic radiation for a long time, which is what might have caused its icy surface to form a crust to protect it. This crust probably kept the lower layers of ice from melting in outer space because it was too cold for them. But as 3I Atlas got closer to the Sun, it slightly heated up on the surface. This caused some gas and dust to escape, but not enough to make the bright comet tail that was seen in Borisov. The faint dust tail also hints that interstellar comets may not all be created equal. While comets in our solar system, such as those originating from the Oort cloud, are typically composed of water ice, carbon monoxide, methane, and other volatile ices, interstellar comets may have a different chemical makeup. For example, 3I Atlas's relatively weak dust tail could suggest that it contains less of the easily sublimating volatile material and more organic rich or rocky material. These could be compounds that do not readily sublimate or that require more intense heating to release gas. Its dust behavior therefore provides a clue that interstellar comets might evolve differently based on their star system origins and the chemistry of their formation environments. The nature of its dust tail may reveal how cosmic ray exposure and the lack of a strong stellar wind in interstellar space have shaped 3I Atlas's surface over time. As 3I Atlas drifted through the Milky Way, it would have been bombarded by high-energy radiation, which can alter the chemical composition of its surface. The organic rich surface materials we observe could be the result of this radiation. This exposure likely caused a gradual build-up of a dark radiation-processed crust that further reduced its cometary activity. The sublimation of 3I Atlas's ices, therefore, was far less dramatic than expected for an object entering the solar system from interstellar space, reinforcing the idea that interstellar comets evolve differently from those in our solar system. It's also possible that the lack of a clear tail is related to how the production of dust changes among cosmic objects. Outgassing is what usually makes comet tails. This is when sun energy heats ices on the surface and makes them melt. But comets like 3I Atlas, which are very quiet, make us wonder if interstellar comets might have different melting rates because they move farther through space. As these things move through the empty space between stars, they probably don't get very hot from a center star. And when they finally pass through a star system, the sun's energy may only slightly warm their surface. This could make the dust and gas come out much more slowly than with comets that are more busy. The way 3I Atlas's dust moves also tells us about its size and makeup. The thin dust cloud shows that 3I Atlas is mostly made up of ices, but it also has a lot of rock material, probably from its parent planetary system. The presence of silicates in the comet's coma adds to this idea. It suggests that 3I Atlas may have been thrown out from a system with a mix of rocks and ice, possibly a differentiated body like a broken moon or planetessimal. This mix of rock and ice could be the reason why the dust cloud isn't as strong and why it hasn't formed a strong tail like comets that move around more. Could it have planetessimal origins? Astronomers are still trying to figure out what 3I Atlas is. One of the most interesting ideas is that it might not be a normal comet, but a planetessimal piece from a bigger broken body. The building blocks of planets are called planetesimals. In their home star systems, gravity pulls or collisions can break them apart. If 3I Atlas is really a piece, it would be a unique chance to study a part of another planetary system that was thrown into space between the stars a long time before it met ours. Planetesimals are small, solid things that form in the early stages of the formation of a planetary system. These rock and ice things are very important for learning about how planets and moons are formed. Around the Sun, there are a lot of planetesimals that have stayed put, like those in the Kuiper belt or the asteroid belt. Some of these bodies are thrown out of their home systems, though, either by violent crashes or by the pull of huge planets. Over time, these planetesimals that were thrown out can move between stars and become cosmic objects like 3I Atlas. The possibility that 3I Atlas is a fragment of a larger planetesimal is supported by several clues in its composition and behavior. First, its chemical mixture of icy and rocky material suggests it may be more complex than a standard comet, which typically consists of volatile ices and dust. The presence of silicate minerals, which form in the inner regions of planetary systems, indicates that 3I Atlas could have once been part of a larger body, perhaps a moon or a planetesimal, where rocky material mixed with ice during the planet-forming process. This kind of material is typical of differentiated bodies, which have undergone heating and compositional segregation, unlike simpler, undifferentiated comets that are made up mostly of primordial ices. Second, the irregular shape and light curve variations of 3I Atlas hint at a fragmented origin. If it were a fragment of a larger body, it is likely to have been shattered by a collision, either with another object or through a gravitational slingshot by a nearby star or planet. The variations in brightness as the object rotates suggest that it is not spherical, but rather elongated or irregular, a common feature of fragments that have been broken apart. This is consistent with the behavior of bodies that have undergone violent impacts, leaving behind debris that lacks the smooth spherical shape seen in intact comets or asteroids. Due to its weak coma and small amount of dust activity, 3I Atlas is not a perfect comet. It probably formed in the outer parts of its home star system, where there are icy bodies. However, cosmic rays have worn away at its surface over time, as it has traveled through interstellar space for a long time. These changes on the surface could have shut off many of the explosive ices below, making it less active than a normal comet. but still holding on to parts of its original makeup. 3I Atlas seems to have escaped the hard conditions of interstellar space, which adds to the idea that it is a strong piece and not a comet that is easily broken up. If 3I Atlas is indeed a planetary fragment, it would have likely been ejected from its home system during an early chaotic phase of planetary formation. Young planetary systems are often unstable, with giant planets migrating inward or outward, disrupting the orbits of smaller bodies and sending planetesimals flying into interstellar space. These early ejection events can be triggered by close encounters between massive planets or the gravitational influence of nearby stars. Over the course of millions of years, these ejected planetesimals drift through the galaxy, carrying material from their home systems to distant regions of space. The path of 3I Atlas, which points toward the Carina and Scorpius regions of the sky, suggests that it may have originated from a star system near these stellar nurseries, regions rich in newly formed stars and planetesimals. The gas and dust in these regions could have interacted with 3I Atlas during its passage, altering its course and slightly changing its velocity, while the exact origin of 3I Atlas remains uncertain. Its path through these regions of space raises the possibility that it was ejected from a system relatively close to a star-forming nebula, where gravitational interactions could have flung it into the void. More research into the surface makeup of 3I Atlas could give us more information about where it came from as a planetesimal. As scientists look at how reflective it is, they can learn more about the materials that make up its surface and how cosmic rays and galactic dust have changed them. For instance, if the object's surface has a lot of carbonaceous chemicals or organic-rich materials, it might be a piece of a carbon-rich planetesimal that used to circle a big planet. These chemicals are usually found at the edges of solar systems, where icy bodies and biological matter mix. Their presence would support the idea that 3I Atlas is a small part of a much bigger, broken world. Is it an interstellar comet or an asteroid? The debate. Astronomers had to decide right away whether 3I Atlas was a cosmic comet or more like an asteroid when it was first found. At first glance, the difference may not seem very important, but it has big effects on how we think about how physical systems form and change over time. There are important differences between comets and asteroids, especially in how they behave and where they come from. By looking at 3I Atlas's traits, scientists are trying to figure out which group it belongs to the most. The most apparent difference between comets and asteroids is activity. Comets are typically composed of a mixture of ices, dust, and volatile compounds that sublimate when they get close to a star, creating the characteristic coma and tail of gas and dust. Asteroids, on the other hand, are rocky bodies that generally remain inert, with little to no visible activity, unless they are struck by another object or show signs of internal fragmentation. At first glance, 3I Atlas seemed to fall into the comet category, as it displayed some faint activity in the form of a dust halo and weak outgassing. However, unlike other comets, such as Comet Borisov, which showed a long, well-defined tail, 3I Atlas's activity was faint and irregular, prompting some astronomers to question whether it was truly a comet at all. While it did not exhibit the typical cometary tail, its weak coma suggested that it might still have some volatile material on its surface. Spectroscopic analysis revealed the presence of water ice and carbon monoxide, both of which are characteristic of cometary bodies, suggesting that 3I Atlas had some comet-like characteristics. The faint outgassing observed could be the result of sublimation, where ice on its surface was heated by the sun as it passed through the solar system, releasing gas and dust. But the fact that it doesn't have a strong, obvious tail like Borisov, or a clear core like most comets in the solar system, brings up important questions. If 3I Atlas was a comet, why didn't it show more outgassing as it got closer to the sun? Its low level of activity could mean that it doesn't have the flammable ices that comets usually have, or that its surface has been protected by a hard crust that formed over its long trip between stars due to cosmic radiation and other space weathering effects. Astronomers also observed that 3I Atlas's orbit did not behave entirely like that of a typical comet either. Most comets follow elliptical orbits that bring them close to the Sun, and then take them back out to the far reaches of the solar system. These orbits are often highly elliptical, with a clear perihelion, closest approach, and aphelion, farthest point. 3I Atlas, however, follows a hyperbolic orbit, meaning it is on a one-way path through the solar system and will never return. This hyperbolic trajectory suggests that 3I Atlas was not gravitationally bound to the Sun and is merely passing through the solar system. In contrast, most comets tend to be bound in elliptical orbits, which could theoretically bring them back to the solar system multiple times. This strange path makes it even harder to put 3I Atlas into a category. Most asteroids are in stable paths. This is especially true in the asteroid belt, which is between Mars and Jupiter, and in the Kuiper belt, which is beyond Neptune. Comets, on the other hand, usually come from the outer solar system, like the Oort cloud or the Kuiper belt. They have very irregular paths that bring them close to the Sun, where they become active. 3I Atlas is not in the solar system and moves between the stars, so it behaves in a way that is somewhere between that of a comet and an asteroid. It doesn't really belong in either group, which is why the argument goes on. The 3I Atlas's surface makes it even harder to classify. Most asteroids, especially carbonaceous ones, are made up of a mix of metals and silicates with only a small amount of flammable materials. On the other hand, comets are mostly made up of ices, dust, and organic substances, and many of these break down when they hit the Sun. 3I Atlas shows liquids like water ice and carbon monoxide, which are common in comets, as well as mineral dust, which is more common on asteroids. Because it is made up of two different types of matter, 3I Atlas may really be a mixed object with traits of both comets and asteroids. Thermal models. How did it survive interstellar travel? People are interested in 3I Atlas's trip from its home system to its short meeting with our solar system. They want to know about its makeup, its path, and how it managed to survive the harsh conditions of interstellar space. Radiation, cosmic rays, and very high temperatures make the space between stars a very empty place. Most things would break down very quickly in this space. Still, 3I Atlas made it through the galaxy's cold and destructive void and into our solar system mostly undamaged. To figure out how it made it through such a long and dangerous trip, scientists need to use thermal models. These are computer studies that try to guess how things like 3I Atlas will respond to radiation, heat, and space weather as they travel between stars. Cosmic radiation is one of the main things that determines what happens to an object like 3I Atlas that is not a star. 3I Atlas would have been hit by high-energy particles coming from all directions as it traveled. Cosmic rays are spread out in outer space. They are made up of charged particles like protons, electrons, and atomic nuclei. These particles move very quickly, almost as fast as light. If they touch something for a long time, they can do a lot of damage to its surface. For 3I Atlas, this attack would have changed the chemicals on its surface, which would have worn it down over time as it moved through the galaxy. Cosmic rays can melt ice, making complex organic substances that make the surface of the item darker. The dark radiation-treated crust seen on 3I Atlas was probably formed by this process. It may have kept the unstable ices below it from being directly exposed to the harsh elements of space. The survival of 3I Atlas in interstellar space depends heavily on how well it maintained its thermal balance throughout its long journey. Objects like 3I Atlas, when they are far from any star, experience extremely low temperatures, often hundreds of degrees below freezing. In such conditions, water ice, carbon monoxide, and other volatile compounds would remain solid, preserving the object's original composition. However, when these objects approach a star, they begin to heat up, and the volatile compounds on their surfaces start to sublimate. In the case of 3I Atlas, the heat it received from the Sun was likely sufficient to cause some sublimation of ices, leading to the faint coma and dust trail it displayed as it passed through the inner solar system. Thermal models predict that objects like 3I Atlas experience an intense thermal shock as they transition from the extreme cold of interstellar space to the relatively warmer environment of the solar system. For instance, as 3I Atlas approached the Sun, the temperature on its surface would have risen dramatically, potentially causing cracks and fractures on its outer crust. This thermal stress could have been one of the reasons why it exhibited weak activity, with only a faint release of gas and dust. The object may have been partially shielded by a thick insulating crust, which helped preserve the volatile ices beneath it, while allowing for limited sublimation in response to the Sun's heat. How fast an object heats up when it gets close to a star is another important thing to think about when modeling its temperature. The surface of 3I Atlas would have been exposed to the Sun's rays because it is a small object. However, its irregular form and size may have caused uneven heating. Smaller objects like 3I Atlas may heat up in spots, unlike larger comets whose surfaces may heat up more evenly. This could cause uneven outgassing and more dust production in those places. This might be the reason why the object's dust trail wasn't as noticeable as Comet Borisov's, which had a more normal comet tail as it moved through the solar system. Cosmic rays also play a significant role in shaping the thermal history of interstellar objects. Over the course of millions or billions of years, these high-energy particles slowly break down the outer layers of a comet or asteroid, creating a darkened, radiation-processed surface that can insulate the more volatile materials beneath. In the case of 3I Atlas, the outer layer of organic-rich materials likely acted as a protective shield for the more volatile ices inside. This protective crust would have prevented rapid sublimation in the absence of strong solar radiation, allowing 3I Atlas to survive the long journey through interstellar space. The amount of biological materials that may have changed during 3I Atlas's time in space is an interesting part of its thermal past. CO2 and other complex chemicals can form on the surfaces of comets and planetesimals due to radiation from space. These molecules being on 3I Atlas adds a new and interesting layer to the idea that objects in the interstellar space could carry prebiotic chemicals. 3I Atlas may have picked up organic materials like those found on comets as it went through space. This could have sent the building blocks of life across the galaxy. It's still not clear how well these organics survived the high temperatures of interstellar travel, but experts are still interested in the idea that they might have been able to stay alive inside the icy shell of 3I Atlas. The trajectory of 3I Atlas also sheds light on the dynamics of thermal equilibrium during its travel. Its hyperbolic orbit meant that it was passing through the solar system at an extremely high velocity, and its brief interaction with the Sun would have been brief enough that it didn't heat up enough to experience dramatic changes. Its rapid passage meant that it was exposed to the Sun's radiation for a relatively short time compared to a typical comet, which spends longer periods in the inner solar system. This reduced exposure time likely kept 3I Atlas from reaching the level of activity seen in other comets, resulting in its faint outgassing. Did it pass through other star systems before reaching us? For scientists, one of the most important things to know about 3I Atlas as it moved through our solar system was if it had been through other star systems on its way. Since 3I Atlas came from between stars, it's likely that it didn't come from a single point in space and travel straight to our solar system. Instead, it probably took a long trip through the Milky Way, possibly going through several stellar neighborhoods on its way to us. Following its path and going around its orbit again might help us figure out if it has passed by other stars, and if so, what that might tell us about the area it went through. Interstellar objects like 3I Atlas are thought to be ejected from their parent star systems during violent gravitational interactions or through the process of planetary migration, where giant planets move through the protoplanetary disk and eject material into space. Once ejected, these objects wander freely through the galaxy, following hyperbolic orbits that are not bound to any star. The trajectory of 3I Atlas has been carefully analyzed, and it's clear that its path is hyperbolic, meaning it is only passing through the solar system and will never return. People are still very interested in the road that led to this point. Astronomers' data on 3I Atlas's path has helped us get a good idea of where it came from, but we still don't know where it went before it reached our solar system. The galaxy is very big and full of stars, so it's very likely that 3I Atlas went through other star systems and stellar regions on its long journey. However, it is much harder to figure out which exact stars it may have passed. The trajectory of 3I Atlas points to a region of space near the constellations Carina and Scorpius, which are home to several massive star-forming regions. These regions are filled with young stars, some of which may have already ejected objects like comets or planetesimals into interstellar space. While it's impossible to definitively trace the object's exact path, simulations based on its current trajectory suggest that it may have passed close to some of these stars, potentially interacting with their gravitational fields. These interactions could have altered the object's course, nudging it toward our solar system. But interstellar space is not empty. It is full with cosmic stuff like molecular clouds, other stars, and the remains of supernovae that happened in the past. It's possible that 3I Atlas went through a lot of different settings along these long journeys. Each one affected its path. The item would have been affected by cosmic radiation, high-energy particles, and dust over time, changing its surface and makeup little by little. Space weather can also leave behind marks that could tell us more about how it moved through other star systems. It's possible that further research into 3I Atlas's chemical makeup could reveal signs of other star systems it passed by, like a cosmic fingerprint that shows where it went. Despite these possibilities, direct evidence that 3I Atlas passed through other star systems is difficult to obtain. The sheer vastness of interstellar space means that the chances of the object passing through a star system with sufficient proximity to alter its course are relatively low. However, simulations of interstellar object trajectories suggest that many of these objects do pass through multiple stellar systems over millions or even billions of years. While 3I Atlas may not have encountered any stars in the immediate vicinity of its path, its journey likely took it through star-forming regions, dense molecular clouds, and other stellar environments that left subtle, albeit significant, marks on its surface. The surface of 3I Atlas is one of the most important things that may help us figure out where it came from. The object's weak activity and light dust halo suggest that it is made up of a mix of ices and organics, some of which may have changed as it traveled through space for so long. As it went through different star systems and cosmic settings, it probably picked up cosmic rays and galactic dust on its surface, which changed the chemicals that make it up. Scientists can study an object's past and find out if it went through other systems by looking for cosmic fingerprints left behind by this process. Why 3I Atlas matters for planetary defense? 3I Atlas is an interesting guest from beyond the stars, and its short trip through the solar system has important lessons for protecting planets. Even though 3I Atlas didn't pose a direct threat to Earth, its visit brought to light some important problems that might appear in the future, especially as it becomes easier to find things in other galaxies. Scientists can improve early warning systems, find better ways to identify cosmic threats, and learn how to deal with them if they ever come our way by studying 3I Atlas's fast speed, odd shape, low level of activity, and fast path. Planetary defense has traditionally focused on near-Earth objects, NEOs, comets and asteroids that orbit within our solar system and occasionally come close enough to Earth to pose a risk. Over the past few decades, astronomers have made significant strides in identifying these objects and predicting their paths. However, interstellar objects like 3I Atlas introduce a new dimension to planetary defense. Unlike NEOs, these objects come from outside our solar system and can approach Earth at much higher velocities. This means they can be harder to detect and track, with much less time available for mitigation efforts. Their fast speed is one of the biggest problems with cosmic objects. Most comets and asteroids move at speeds of 20 to 30 kilometers per second, but interstellar objects like 3I Atlas can move at speeds of tens of kilometers per second. This object was moving at about 60 kilometers per second as it got closer to the Sun. Because they are moving so fast, they are hard to spot early on, and it's hard to tell when they will hit because the time for view is so small. Astronomers only have a short amount of time to study an object's path and evaluate any possible danger as it moves faster through the solar system. The hyperbolic trajectory of 3I Atlas means that it was on a one-way path through the solar system, never to return. While this fact eliminates any direct threat, it also means that we would have very little time to act if a similarly fast-moving object were on a collision course with Earth. A high-speed interstellar object could potentially impact our planet with little or no warning, leaving limited time for mitigation strategies such as deflection or even evacuation. This highlights the importance of not only detecting such objects early, but also developing advanced methods to deal with them. Finding things in interstellar space is also hard. Based on 3I Atlas, these objects are very dim and are often hard to see against the background of stars. With the technology we have now, they are hard to find because they don't give off much gas, leave behind much dust, and are small. A lot of these things might be moving through the solar system without being seen, especially if their paths don't cross Earth or other places of observation. New sky surveys like Atlas and Pan-STARRS have made it easier to find NEOs, but they are mostly built to find objects that are close to Earth. It is much harder to catch interstellar objects that pass far from Earth. 3I Atlas wasn't seen until it had already gone by near perihelion. This shows how important it is to have better, more sensitive methods to find these things sooner. While learning things like the 3I Atlas helps us better understand how to deal with possible threats, it also helps us improve our ability to find them. If an interstellar object ever came close to hitting Earth, the current planetary defense plans might not work for faster interstellar objects. For example, the kinetic impactor method, where a spacecraft hits the object to change its course, or nuclear deflection, might need to be changed. Unlike asteroids that move more slowly, these objects move so fast that they might need different ways to hit, or even different types of vehicles that are made to deal with objects moving at such high speeds. Studying 3I Atlas's size, makeup, and material strength can help these plans by giving us useful information about the kinds of things we might face in the future, and how to change how we defend our world. Understanding the physical features of cosmic objects also helps us make better models of space weather. A lot of the time, these things bring dust, organic molecules, and even pieces of planets that could have made it through the hard conditions of space. These things might have important details about how chemicals work in other star systems, which could help us figure out where life might start in other parts of the galaxy. Not only are we learning how to find and possibly avoid future threats by studying things like 3I Atlas, but we are also learning more about the universe as a whole. Could we send a probe? Mission feasibility studies. The discovery of 3I Atlas opens up an exciting new way to explore space, sending a spaceship to interstellar objects as they pass through our solar system. Even though 3I Atlas's short trip didn't leave time for a straight mission, it makes us wonder if we could one day capture such objects and send a probe to learn more about them. Sending a spaceship to a visitor from another star system is both an exciting and difficult idea. To do it, you would need to use cutting-edge technology, come up with new ways to move the spacecraft, and carefully plan how to catch things moving at very high speeds. One of the most obvious challenges to sending a probe to an interstellar object like 3I Atlas is its speed. As mentioned earlier, 3I Atlas was traveling at about 60 kilometers per second, far faster than any spacecraft we have ever built. The challenge here is that typical spacecraft in the solar system are designed to travel at much slower speeds, typically in the range of 10 to 20 kilometers per second. This means that to catch up with an object like 3I Atlas, a probe would need to be equipped with a propulsion system that could either match or exceed the velocity of the interstellar object. To catch up with an object like 3I Atlas, a spacecraft would need to adjust its orbit within the solar system to align with the trajectory of the interstellar object. The spacecraft would likely need to use a series of gravity assists from planets, especially the gas giants like Jupiter and Saturn, to increase its speed. These gravity assists, which have been used in many successful space missions, allow spacecraft to pick up additional velocity by flying close to a planet and utilizing its gravitational pull to slingshot the spacecraft forward. While gravity assists are a powerful tool for increasing velocity, they still have limitations, especially when dealing with an object as fast as 3I Atlas. In fact, the most advanced spacecraft ever launched, such as NASA's Parker Solar Probe, which was designed to travel at record-breaking speeds of around 700,000 kilometers per hour, is still far too slow to catch up with an interstellar object moving at tens of kilometers per second. For that reason, a more advanced propulsion system would likely be needed to successfully intercept an object like 3I Atlas. Interstellar journeys could use technologies like the solar sail. Solar sails are big, light sails that are made to catch the speed of photons from a star. This way, they can keep going faster without using fuel. With this technology, a spaceship might be able to slowly pick up speed until it can catch an object traveling between stars. The concept of solar sails for traveling between stars is not just an idea. Projects like Breakthrough Starshot want to use tiny light probes propelled by laser beams to reach speeds of up to 20% of the speed of light. This could allow them to reach nearby star systems within a human lifetime. A similar idea could be used to catch interstellar objects moving quickly, like 3I Atlas. Another option for accelerating spacecraft to the necessary speeds is ion propulsion. Unlike chemical propulsion systems, which rely on the expulsion of gases to create thrust, ion drives work by using electricity to ionize a fuel, typically xenon, and expel the ions at extremely high velocities. While ion drives provide very low thrust, they can operate for extended periods, allowing spacecraft to gradually accelerate over time. The Dawn mission to Vesta and Ceres demonstrated the potential of ion propulsion in solar system exploration. If adapted for interstellar missions, ion drives could provide a continuous, though slow, acceleration, potentially allowing a probe to catch up with an interstellar object over the course of many years. Even with these advanced propulsion technologies, timing is everything. 3I Atlas passed through the solar system so quickly that by the time it was detected, it was already far beyond the point where a spacecraft could intercept it. However, this presents a valuable lesson for future mission planning. The earlier we detect interstellar objects, the more time we will have to plan and launch a mission. As detection technologies improve with upcoming sky surveys like the Vera Rubin Observatory, future interstellar objects could be spotted much earlier, giving us more time to prepare for potential missions. How long the mission lasts is another big problem. Interstellar objects move through the solar system so quickly that they are usually only seen for a few months at most as they pass through. It would most likely take years or even decades to run after one of these things. Because their paths aren't always clear, spaceships would have to be very strong and able to make long trips through space, dealing with radiation, micrometeoroid hits, and extreme temperatures. For this to work for such long amounts of time, the probe might need new materials, more advanced spaceship systems, and new ways of doing things. What can its trajectory teach us about galactic dynamics? 3I Atlas's trip through our solar system is a unique chance to learn not only about the object, but also about how the galaxy works as a whole. Astronomers can learn a lot about how interstellar objects move, the structure of the galaxy, and the forces at work in the Milky Way's gravitational field by looking at 3I Atlas's path and how it interacts with the solar system. Because it moves so quickly, scientists can test ideas of how stars move, how galaxies interact, and the basic processes that control how things move between stars. The parabolic path of the 3I Atlas is one of the most interesting things about it. Most things in our solar system move in circular paths that are limited by the Sun's gravity. 3I Atlas, on the other hand, is only going one way through the solar system. Its parabolic path means that the Sun's gravity can't pull it in, and it will take it out of the solar system and never come back. Astronomers can study how interstellar objects move through the galaxy and what forces shape their paths by keeping track of its speed and figuring out its exact orbit. The first key insight that 3i Atlas provides about galactic dynamics is how stellar motions affect the trajectories of interstellar objects. The object's path suggests that it came from a distant region of space near the Carina and Scorpius regions, areas filled with young star-forming systems. This trajectory indicates that 3i Atlas may have been ejected from a stellar nursery or a young stellar system, where gravitational interactions could have played a key role in sending it into interstellar space. The passage of 3i Atlas through our solar system shows how objects from distant regions of the galaxy can be deflected and sent on high-speed, unpredictable orbits influenced by the gravity of massive stars or other objects along the way. By tracing the object's path backward in time, astronomers can also gain insights into the distribution of interstellar objects across the Milky Way. 3i Atlas's high velocity suggests that it originated from a region of space where stars are more spread out, possibly in the outer reaches of the galaxy. The motion of the object can be compared to simulations of stellar migrations, allowing scientists to test the predictions of galactic evolution models. If more objects like 3i Atlas are discovered in the future, these models can be refined, improving our understanding of how objects are ejected from star systems and how their paths are shaped by the gravitational influences of nearby stars, molecular clouds, and galactic structures. The path of 3i Atlas also makes us think about how galaxies communicate with each other. The Milky Way is not a fixed structure. It is a moving system where stars, gas clouds, and dark matter all interact with each other through gravity. As stars move around the center of the galaxy, they interact with each other by pulling on each other's gravity forces. These interactions can throw things out into outer space when planetary systems become unstable. 3i Atlas may have been affected by these kinds of interactions during its journey through the solar system. It could have been from a close brush with another star, or from changes in gravity caused by the movement of gas and dust in the galaxy. As stars move through the sky, their gravitational fields can change the tracks of things nearby, possibly sending them on trips between stars. The study of interstellar objects like 3i Atlas also allows astronomers to explore the history of galactic formation. Most of the objects in the Milky Way, planets, asteroids, and comets, are bound to stars in stellar systems. But the fact that objects like 3i Atlas can be ejected from their home systems and travel through the galaxy suggests that galactic dynamics is a far more fluid process than previously thought. The ejection of objects into interstellar space may have been a common occurrence in the early history of the galaxy as stellar systems formed and evolved. Studying the paths of these interstellar objects allows us to peer into the past and understand the forces that shaped the early dynamics of the Milky Way. Tracking the speed and direction of 3i Atlas as it entered the solar system provides valuable insights into the galactic gravitational fields that affect objects as they move through space. The object's rapid movement through the solar system indicates that it came from a region of the galaxy with low gravitational influence, meaning it was traveling through space far from the gravitational pull of major stars or stellar clusters. By measuring how the solar system's gravity interacted with 3i Atlas, scientists can improve their understanding of how objects are affected by external galactic forces, which can inform models of stellar dynamics and galactic motion. In the bigger picture of how galaxies move and change over time, studying 3i Atlas may also help us understand how interstellar matter is spread out across the galaxy. As the object moved through the solar system, scientists carefully watched how it reacted with the cosmic radiation, interstellar gas, and the solar wind. These measures could help figure out how dense the material between the stars is along the object's path, which would tell us more about the galaxy medium. By studying these kinds of objects, we'll be able to make a map of how dense the gas and dust are across the Milky Way. This will help us learn more about the conditions between the stars. Micrometeorite trails. Did it leave debris in the solar system? If 3I Atlas left any junk behind as it went through our solar system, that is one of the most interesting questions about it. 3I Atlas is an interstellar object that comes into our solar system from a faraway star system. It may have stayed mostly intact during its trip through the solar system, but the fast speed may have caused micrometeorites and dust to fall off of it. It's possible that these tiny pieces have hit Earth's atmosphere or are spread out in the solar system, adding to the cloud of cosmic dust that surrounds and goes beyond our world. How cosmic objects like 3I Atlas connect with the space they pass through is one of the most interesting things to study about them. As 3I Atlas got closer to the Sun, it was exposed to more energy from the Sun, which probably caused some of its top material to melt away. When flammable ices and other materials are exposed to the Sun's heat, they melt and turn into gas and dust. This process may have let some gas and dust escape from the surface. This dust could have spread along its path, leaving behind a trail of micrometeorites. These micrometeorites are essentially tiny fragments of rock and ice that break off from the object as it passes through space. The high-speed passage of 3I Atlas would have subjected it to extreme conditions, including intense heating from the Sun. As these objects travel through the solar system, they are also exposed to cosmic rays, which can alter their physical properties over time. The intense solar radiation would have caused 3I Atlas to shed material, which would have created a faint dust trail behind it. Some of these particles, particularly the micrometeorites, could have entered Earth's atmosphere. As they traveled through space, these tiny fragments of 3I Atlas would have been dispersed along its path, potentially becoming part of the cosmic dust cloud that surrounds our solar system. While most micrometeorites are too small to be detected by the naked eye, they play an important role in our understanding of the cosmic environment. NASA's missions to study space dust have shown that cosmic dust contributes to the formation of planets, moons, and other celestial bodies. And even the dust particles that enter Earth's atmosphere provide valuable information about the objects they come from. The particles left behind by 3I Atlas may also contribute to Earth's meteor shower cycles, especially if the object's path intersects the Earth's orbit. For example, in August, the Earth passes through the debris of Comet Swift-Tuttle, which causes the Perseid meteor shower. If 3I Atlas left behind any dust trail on its way through the solar system, this could have added to the interstellar dust that contributes to these annual meteor showers. However, the time window during which the object passed through the solar system was too brief for a significant impact on meteor shower patterns. Although it is hard to say for sure how much debris 3I Atlas left behind, looking at the debris that comets and asteroids leave behind can help us guess how much 3I Atlas may have contributed. Since comets like Borisov have been shown to release a lot of dust and gas as they move through the inner solar system, it seems likely that 3I Atlas, which is mostly made up of ice, would have also released some dust. 3I Atlas, on the other hand, didn't give off as much gas as comets in our solar system, so it's possible that the amount of dust it shed was pretty small. Even if the amount of debris was small, it is possible that 3I Atlas contributed to the interstellar dust that exists in the solar system. These particles, while difficult to detect, provide important clues about the material composition of objects outside our solar system. By studying the dust trail left behind by objects like 3I Atlas, astronomers can learn more about the composition of other planetary systems and the interstellar medium. The study of these materials can also provide insight into the processes that take place in star-forming regions, as the dust particles might carry chemical signatures of prebiotic molecules, which could be the building blocks for life elsewhere in the galaxy. What does its path tell us about the population of interstellar objects? 3I Atlas's journey through the solar system has raised important questions about the types of interstellar objects that may be in our galaxy. 3I Atlas is the second proven cosmic object to pass through our solar system, after Oumuamua. It gives us a rare look into a part of the universe that hasn't been studied much: how things move between stars. Scientists can learn more about how often, where, and how these brief space visitors act by looking at the path of 3I Atlas. The fact that 3I Atlas was detected at all is significant. Its passage, along with the detection of Oumuamua in 2017, suggests that interstellar objects may not be as rare as once thought. The high-speed trajectory and relatively short time of observation, about a few months, indicate that many such objects could be passing through the solar system unnoticed. Sky surveys like Atlas and Pan-STARRS are becoming more adept at spotting these visitors, but the true population of interstellar objects remains largely unknown. In fact, 3I Atlas may have been just the tip of the iceberg, and its detection suggests that many more interstellar objects may be moving through the galaxy yet to be observed. If 3I Atlas is any indication, interstellar objects may be more common than previously believed. It's likely that many objects, like planetesimals, comets, and asteroids, are flung out of their parent systems through the process of planetary migration or stellar interactions. These objects can wander through the galaxy for billions of years, gradually drifting into the gravitational reach of other star systems. The discovery of 3I Atlas, combined with future detections, could help astronomers estimate the total number of interstellar objects in the galaxy and provide a better understanding of how often they pass through our solar system. Along with studying the population of interstellar objects, astronomers are also improving theories of how the galaxy moves. Looking into how these things move and interact with the Sun and planets can help us understand how gravity works in the Milky Way. For instance, the fact that 3I Atlas was moving at speeds much faster than most objects in the solar system says that these objects probably come from parts of the galaxy with weak gravity, far from the thick gravity-bound areas near stars and planets. This backs up the idea that many of these objects are thrown out from the edges of star systems, maybe after interacting with big planets or running into stars. The detection of 3I Atlas and its trajectory also helps scientists estimate how interstellar objects interact with the solar system. Objects traveling at speeds faster than solar system comets can be difficult to detect, as they pass by the Sun too quickly to be observed for extended periods. As more interstellar objects are discovered, the data gathered from their paths will help astronomers improve their models of how these objects behave as they approach stars, how their trajectories are altered by gravity, and how they interact with other bodies in the star system. Could it be captured? Long-shot scenarios. Getting an object like 3I Atlas from between the stars seems like something out of science fiction. The Sun and the planets in the solar system don't have the power to quickly catch things that are moving at very fast speeds, up to 60 kilometers per second, like the 3I Atlas. Most of the time, these things are on hyperbolic paths, which means they are just going through and will never come back. But is it possible to bring an object from between the stars like 3I Atlas into orbit around the Sun, Earth, or even one of the planets? In theory, yes, but the chances of something like that happening are very small. To understand why capturing 3I Atlas would be difficult, it's important to consider the object's velocity. Unlike asteroids or comets that orbit the Sun in elliptical orbits, interstellar objects like 3I Atlas are traveling at far higher speeds and are not bound to the Sun's gravity. They are simply passing through the solar system on a one-way journey. For an object to be captured into a stable orbit around the Sun or any planet, it needs to lose a significant amount of its kinetic energy in a process known as gravitational capture. The best-known example of a body being captured into a gravitational orbit is Comet Borisov, which was the first interstellar comet to be detected in 2019. However, even Borisov's trajectory was not entirely captured by the Sun. It followed a hyperbolic trajectory meaning it passed through the solar system without being permanently bound by the Sun's gravity. To capture such an object would require it to lose enough speed, an almost impossible feat when dealing with high-velocity interstellar objects like 3I Atlas. The most likely way for an object from between stars to be pulled into orbit would be for it to interact with a large planet like Jupiter or Saturn gravitationally. The gravity pulls of these gas giants are so strong that they might slow down an object moving by. If everything was just right, like the object's speed and path matching up perfectly with the planet's gravitational pull, it might be able to be caught in a brief circle around the planet, or even the Sun. However, the chances of such an event happening are very low, because so many things would have to be in the right place for it to happen. The scenario of capturing an interstellar object into a solar orbit is also complicated by the fact that interstellar objects, especially those like 3I Atlas, are often moving too fast for a single gravitational encounter to significantly alter their trajectory. Even with a large planet's gravitational influence, these objects are typically still moving too fast to be slowed down enough to remain in orbit. This limits the likelihood of capturing these objects into stable orbits, at least without some additional forces or mechanisms at play. Using a complex set of gravitational assists to catch an interstellar object is another option. This is similar to how spaceships use gravity to speed up their travel around worlds. In theory, a spaceship could use the gravity of several planets to slow down an object in space between the stars. By going close to a number of planets over and over, the object could slowly slow down until it reached a stable orbit. To pull this off, it would need to be carefully coordinated, take a very long time, and probably involve more than one ship. This is still an interesting idea in theory, but it's hard to make happen because it would take a lot of energy and very accurate time. The best chance of catching an object like 3I Atlas might be if it slowed down a lot as it went through the solar system. This could happen through multiple gravitational interactions with planets or even stellar interactions if it went by another star system on its way to the solar system. But even in these situations, the item would still have to slow down a lot, which would be hard to do. 3I Atlas as a time capsule of exoplanetary systems. 3I Atlas is like a cosmic message because it lets us study the building parts of planetary systems other than our own. The most interesting thing about 3I Atlas is that it might be able to store samples from an exoplanetary system that formed in a different part of the galaxy in perfect condition for a long time. 3I Atlas is traveling through space, carrying a record of the chemical and physical conditions from the faraway star system it came from. This gives us a unique look into the processes that shape other worlds. Interstellar objects like 3I Atlas are often the remnants of much larger bodies, planetary fragments, planetesimals, or even pieces of shattered moons or planets. These fragments, which are ejected from their home systems through gravitational interactions or stellar encounters, carry material that has never been exposed to the conditions of our solar system. As 3I Atlas passed through the solar system, astronomers were able to study the chemical composition of its surface, which revealed the presence of water ice, carbon monoxide, and other volatile compounds. These elements are common in the outer regions of star systems, suggesting that 3I Atlas may have originated from a cold, distant region of its parent system, much like comets in our own solar system. But 3I Atlas is important for more than simply its chemical makeup. Things like 3I Atlas are cosmic treasures that hold information about how things were in the star systems where they came from billions of years ago. Some of these factors could be the molecular cloud's temperature, density, and makeup, which is where the star system began. 3I Atlas has been traveling through interstellar space for billions of years without changing much. Because of this, it can tell us a lot about the setting in which it was formed. The sun's heat, cosmic rays, and other forces have changed other objects in the solar system, but 3I Atlas may have stayed the same in a way that other objects in the solar system have not. By studying the surface of 3I Atlas, astronomers can also infer the chemical processes that took place in its parent system. The presence of organic molecules, such as amino acids or other prebiotic compounds, would suggest that the environment in which it formed may have been conducive to the development of life. If 3I Atlas carries complex organic compounds, much like some comets in our solar system, it could serve as a time capsule that contains the building blocks of life from another corner of the galaxy. This reinforces the idea that organic molecules may be widespread throughout the universe, carried by interstellar objects like 3I Atlas across vast distances between stars, potentially seeding life on other planets. The data collected from 3I Atlas could also offer insights into the processes of planet formation in other star systems. The presence of silicates and other rocky materials on the surface of 3I Atlas suggests that it may have once been part of a larger planetary body, possibly a moon or planetessimal. By analyzing its composition, scientists can learn more about the types of materials that are common in the early stages of planet formation in other star systems. This could help astronomers understand the conditions necessary for the creation of rocky planets and moons, and how these planets evolve over time. 3I Atlas is a lot like a fossil from another solar system. It shows how a faraway star system formed. Things like 3I Atlas can help us see into the past and guess what other worlds might have been like when they were first joining the universe. We are just starting to learn about interstellar objects, but as more are found, like 3I Atlas, we will be able to get a better idea of the many different types of planetary systems that exist in the universe. For planetary scientists, 3I Atlas is a goldmine. It provides a rare opportunity to study material from a system that is likely completely different from our own. By examining the chemical and physical characteristics of the object, we can gain insights into the kinds of star systems that exist beyond the solar system: hot stars, cool stars, and everything in between. By comparing the properties of objects like 3I Atlas to those in our solar system, scientists can begin to build a better understanding of how planetary systems evolve and how they differ from one another in terms of their composition, structure, and potential for hosting life. Why interstellar objects are important for life-building theories. Finds of cosmic objects like 3I Atlas have huge effects on how we think about life in the universe. These things, which move between star systems, might hold important hints about how life began on other planets besides Earth. Scientists can look into the chance that interstellar visitors like 3I Atlas might move organic compounds, which are the building blocks of life, over very long distances by studying their chemical makeup. The Panspermia hypothesis says that life-building materials could be sent between stars by cosmic objects moving around. This could change how we think about how life started on Earth, and maybe even in other parts of the universe. Chemical makeup is one of the main reasons why interstellar objects like 3I Atlas are so important for ideas about how life began. Like other things in the space between stars, 3I Atlas is made up of ice, dust, and rocks. The fact that it had liquid substances like water ice, carbon monoxide, and organic molecules in it suggests that it may have carried amino acids, nucleobases, and other complex carbon-based molecules that are used for life. These molecules are the building blocks of life, and the fact that they are found in interstellar objects makes it more interesting to think that these objects might carry the building blocks of life to planets and moons all over the galaxy. The idea of panspermia, which suggests that life or its building blocks can travel between planets and even stars, has long been a topic of debate in the scientific community. Interstellar objects like 3I Atlas offer a new avenue of exploration for this hypothesis. As these objects travel through interstellar space, they could carry organic molecules or even prebiotic compounds, providing a potential mechanism for how life could spread between star systems. If life or the necessary components for life exist elsewhere in the galaxy, interstellar objects could be the means by which life is transported, allowing it to potentially thrive on distant planets or moons. The study of comets in our own solar system is a strong piece of proof for the panspermia theory. Comets from the Kuiper belt or the Oort cloud, for example, have complex organic molecules on their surfaces. These molecules are thought to be necessary for life. It is possible for comets to carry biological substances like amino acids when they move through the inner solar system. The NASA Stardust mission that took samples from Comet Wild 2 actually found complex amino acids, which are the building blocks of proteins. It's possible that interstellar objects like 3I Atlas, which are thought to have similar makeups, could also carry the same kinds of biological molecules. They might even be carrying material that is even older or hasn't been affected by a nearby star. If 3I Atlas or other interstellar objects contain prebiotic material, it would also suggest that the chemical processes that lead to the formation of life's building blocks could be widespread throughout the galaxy. In other words, the raw materials for life may be abundant in the universe, and the conditions necessary for life may be more common than we previously thought. Interstellar objects may carry with them molecules that could kickstart the development of life on distant planets, just as life on Earth may have started with organic molecules brought here by comets or meteorites billions of years ago. The study of interstellar objects gives us insight into the formation of planetary systems and the role that interstellar dust plays in that process. As 3I Atlas passed through the solar system, astronomers noticed that it was coated in a thin dust cloud, which may have been released during its journey through space. This dust, composed of small grains of organic material, could provide clues about the pre-planetary environments of other star systems. If interstellar objects like 3I Atlas carry dust particles with organic compounds, it suggests that such material may be common throughout the galaxy and could be incorporated into the formation of planets and moons in other star systems. The discovery of water ice on 3I Atlas adds to the notion that things in the interstellar space may have helped planets form liquid water, which is necessary for life as we know it. In the early stages of a planet's growth, icy objects like comets and planetesimals may crash into it, bringing water and volatile chemicals that are needed to make the environment habitable. As with comets, 3I Atlas may have helped bring water and organic molecules to young planets. This is similar to what comets and asteroids are thought to have done in the early solar system. Could it break apart? Tidal stresses on its journey past the Sun. As 3I Atlas moved through the solar system, some people wondered if its fast speed would put too much stress on its structure and cause it to break apart. Scientists have seen other objects in the galaxy before, but this one was unique because of its speed, path, and interactions with the Sun's gravity. This made it a good example of how tidal stresses could affect an object in the galaxy. The object was moving very fast, and the Sun's gravity made conditions that could possibly break up a less strong object. Tidal forces arise from gravitational gradients, the difference in gravitational pull that different parts of an object experience when it moves through a varying gravitational field. As 3I Atlas approached the Sun, it passed through a region of space where the Sun's gravity would pull more strongly on the side of the object closest to the Sun and more weakly on the far side. This difference in force could have caused significant stress on the object's structure, especially if it was weak or had an irregular shape. The potential for 3I Atlas to break apart was a concern because, like other interstellar objects, it likely had no natural protection from the Sun's gravitational forces. Objects like comets and asteroids in our solar system often experience tidal stresses, particularly during close encounters with planets. When an object like 3I Atlas passes within a certain distance from the Sun, it experiences intense tidal forces, which could lead to cracks, fragmentation, or even complete disintegration if the object's material strength is insufficient. But 3I Atlas didn't seem to be falling apart in a way that would be really bad. 3I Atlas didn't break apart like some comets do when they get too close to the Sun. Its activity stayed low, which suggests it wasn't under as much tidal stress as more unstable bodies. Its weak outgassing and lack of a noticeable tail could mean that it stayed mostly intact, despite the forces that were working on it. It might have been better able to handle the forces of the tides because it was mostly made up of rocks and ice instead of free, fragile ices like most comets are. The next ones to come. Are we ready for more interstellar visitors? 3I Atlas's trip through the solar system was a unique event that gave us a glimpse into the interesting world of objects in space between the stars. But 3I Atlas wasn't traveling by itself. It's just one example of a cosmic visitor that could come through our solar system in the future. The finding of 3I Atlas has made us think about how ready we are for these kinds of events, and how we can better study and plan for future interstellar objects. Advances in astronomical surveys and technology, however, are making it more likely that we'll detect future interstellar visitors earlier. Observatories like Pan-STARRS and the Atlas survey are now actively scanning the sky for fast-moving objects. Moreover, next-generation telescopes like the Vera-Rubin Observatory, LSST, will vastly improve our ability to monitor the sky for potential interstellar objects. These surveys will increase our chances of spotting such objects early, giving us more time to study their trajectories, and possibly send spacecraft to observe them up close. It is very important to find future cosmic objects, but it is also very important to know what to do once they are found. 3I Atlas shows that these items are moving very fast, which makes it hard to catch and study them. Preparing for the coming of interstellar objects is a very important job as we continue to work on planetary defense systems and space exploration technologies. We need to improve the propulsion systems of our spaceships so they can handle things going much faster than the speed of light in our solar system. Technologies like ion propulsion or solar sails could be very useful for sending robots to study visitors from other stars. Interstellar objects present scientific opportunities that should not be overlooked. 3I Atlas's brief passage allowed scientists to gain a snapshot of an object from another star system, and in the future, we may have the chance to gather even more data. Interstellar objects may carry chemical signatures that provide insights into the composition of other star systems and exoplanetary environments. Their study could reveal the origins of organic molecules, the processes of planetary system formation, and even offer clues about the possibility of life beyond Earth. We can expect that more cosmic objects will be found in the future. As our tools get better at finding them, the next ones might be found with even more advanced tools and tracked with a lot more accuracy. We are moving into a time when exploring other stars might not just be a fantasy, but a real possibility. Future space trips could study these cosmic visitors if they are well planned. This would give us new information about the chemistry, dynamics, and past of other star systems. We learn more about the universe and our place in it, as we find and study more cosmic items like 3I Atlas. These visitors from space not only help us learn more about the world, but they also push the edges of what we think we can do in science and technology. The next time something from between the stars comes our way, we'll be better prepared to study it, and maybe even send a probe to find out where it came from. Don't forget to subscribe if you want to learn more about the secrets of the universe with us. You never know what cosmic wonders we'll find next.